Uma história que começou em 1963. Com décadas dedicadas ao desenvolvimento de processos, produtos e embalagens, o Instituto de Tecnologia de Alimentos não mede esforços para se manter como referência no setor alimentício, não só no Brasil, como no mundo. Por entender a importância da inovação e segurança de alimentos, bebidas e embalagens para o consumidor, o ITAL pesquisa e presta assessoria técnica, visando a eficácia e padrões mínimos de qualidade. Além de estar atento aos diferentes perfis de consumidor, o Instituto atua sempre com ética e respeito ao meio ambiente, priorizando a análise crítica para acompanhar a evolução tecnológica e de mercado. As atividades do ITAL são divididas em 3 grandes áreas. A tecnologia é desenvolvida e aplicada nas unidades especializadas em carnes, cereais, chocolates, balas, confeitos, produtos de panificação, laticínios, frutas, hortaliças e engenharias de processo. A ciência e a qualidade são prioridades dos laboratórios de análises químicas, físicas, sensoriais e microbiológicas. A embalagem é o foco que abrange todas as classes e diferentes gerações. São décadas de constante reinvenção, aprendendo e ensinando, décadas de reconhecimento com a bagagem do passado e a modernidade do presente. Com funcionários qualificados, clientes, parceiros e fundações de apoio, o ITAL tornou-se fundamental no setor de alimentos, bebidas e embalagens.
O FORC é um centro de pessoas, que é um centro que agrega pessoas que trabalham, que desenvolvem pesquisa aplicada em diversos pontos da ciência do alimento e da nutrição.
Já se pensava em fazer um centro de alimentos dentro da USP. E a gente achava que a USP, se ela unisse todos os fragmentos, todos os grupos que trabalham com alimentos numa única coisa, nós ficaríamos invencíveis.
Por que não? Por que não fazemos esse projeto, né? E aí nós começamos a conversar e foi um longo processo, porque foram 2 anos para a FAPESP decidir que nós tínhamos expertise suficiente para ter um centro.
A ciência do alimento, a ciência da nutrição, ela é multidisciplinar por definição. Então eu costumo brincar sempre que o mundo tem 9 bilhões de especialistas em ciência de alimentos. Todo mundo entende de alimentos, porque todo mundo come. Existe uma frase famosa do Luiz Fernando Veríssimo: o poder acaba, a visão acaba, o sexo acaba, mas a fome continua.
Uma das coisas que a gente realmente mostrou é que esse tema tem uma importância capital para o país. 30%, quase 40% do nosso PIB vem justamente desse setor, do setor da agricultura, do setor de alimentos. E isso daí tem um reflexo direto, nutrição, para a população.
Nós podemos, em parceria com a indústria, desenvolver projetos que sejam cientificamente de alto padrão, aplicáveis para a indústria que beneficiem a sociedade.
A pós-graduação é importantíssima porque a maior parte justamente de toda a pesquisa que é feita, ela é feita no laboratório por pós-graduandos. Quer dizer, os mestrandos e doutorandos, eles formam a maior parte, vamos dizer assim, dos nossos recursos humanos. Um recurso humano altamente especializado.
Hoje nós temos no FORC 30 jovens pesquisadores trabalhando com a gente e nós conseguimos chamar inclusive pesquisadores do exterior.
A gente percebe que existe um avanço considerável em quantidade e em qualidade também.
Uma das coisas que também a gente quer muito é que a gente tenha essa parceria com universidades e institutos de pesquisa mundiais que trabalhem com alimentos e nutrição. E isso está acontecendo de maneira bem forte.
Se vier uma indústria aqui dizendo que quer desenvolver alguma coisa, quer aprofundar um determinado tema, nós temos as competências aqui para ajudar.
Dentro de uma universidade, dentro de um laboratório, você tem a condição de trazer aquilo lá, aquela ideia, torná-la realidade. E por isso que nós somos apaixonados pelo nosso trabalho.
Eu acho que inovação é quando você vê alguma coisa de um jeito diferente do que os outros veem.
Nós criamos lá embaixo um laboratório que é de primeiríssimo mundo e a gente consegue fazer pesquisas de altíssima qualidade.
Essa é a nossa pretensão, que a gente tenha um centro de pesquisas dentro da Universidade de São Paulo que seja independente.
Consolidar o grupo e ir para frente daí. Se tornar uma referência dentro do universo de alimentos e nutrição para o país e para o mundo.
Nós queremos continuar formando gente muito boa, mas nós queremos formar gente muito boa e produzir ciência muito boa. E como é que a ciência é muito boa? A ciência do 1970 não serve mais. A ciência do 2017 hoje ela é toda integrada, ela é toda colaborativa, ela é toda multidisciplinar, ela é toda sinérgica. O nosso centro ele está no momento certo funcionando dessa forma.
Olha, aquilo que está na nossa missão, viu? Ciência para melhorar a vida.
Each time there is a contamination in food or beverages, the public is made aware. What they don't see is you, mitigating risks every day, taking difficult decisions and making our food as safe as possible. Because you take your job as seriously as we do. With over 350 years experience in highly regulated industries, we understand the importance of reliability and efficiency in your lab. So be it to verify existing methods, stay on top of changing regulations, or to adopt the newest technologies. You can find it all on sigmaaldrich.com. Tailored products for each step of your workflow available on our website. We have products that are suitable for microbial and analytical needs in the crucial step of sample preparation. We have solutions for the most routine sample analysis to advanced genetic detection, such as the Assurance GDS for rapid pathogen detection, often used to test for E. coli in beef. And we support you with a complete set of services and specialists. Our experts are here to improve your day-to-day work with 4 dedicated portfolio brands: Millipore, Sapelco, Sigma Aldrich, and MilliQ. All these products can easily be ordered on our website so that you can focus on making sure that every sip, every bite is safe because it's been tested by you.
A very good morning, everyone in the Americas, and a very good afternoon for the people around Europe, and a very good evening for the people in the East, and even around Oceania. It's almost night. We are connected here with a lot of different people from all over the world in this great webinar that we'll have this morning, evening, and afternoon. My name is Marcel Swietering, and I'm the chairman of the Icmsf, and the other person that you see on the video is Leon Gorres, and he's the secretary of the Icmsf. And we would like to open this session by telling you something about the Icmsf, and then we'll present you the first start of this program and lead you to some presentations. So the International Commission on Microbial Specifications for Food forms part of the International Science Council, and the International Science Council has a subgroup which is called the International Union of Microbial Societies, and the Icmsf is one of these societies. And the Icmsf produces books, position papers, advices to governments and to Codex and to the FAO WHO. And our mission is to be a leading source for independent and impartial scientific concepts that, when adopted by government agencies and industry, will reduce the incidence of microbiological foodborne illnesses and food spoilage worldwide and facilitate global trade. And that shows the 2 aspects that we consider: public health on the one side and fair trade in our world on the other side, also related to fair trade and food security. The Commission consists of 20 food microbiologists from 14 different countries. And you can see here the different countries where we come from. And they apart from coming from different countries over the world, we also have a broad professional background. People do work at governments or at academia or in food industry. And the participants and the commission members are selected for their technical expertise, and they are definitely not national delegates. We look over the world for people that have the good backgrounds, and we try to get people from all parts of the world, but it's not that we have really national delegates. Several people can come from one country, for instance. Also, we work with an extensive network of subcommissions, consultants, and experts. All the work that we do is voluntary and without honoraria. And we do give recommendations, but like the word recommendation says, they don't have an official status. We recommend things in our advices, in our position papers, and in our books, but they have not an official status. One important aspect of the Icmsf are its subcommissions, and the Icmsf subcommissions promote the Icmsf activities among food microbiologists in their region, and they facilitate the communication worldwide. And subcommissions have been also highly useful in translating and communicating the Icmsf concepts applicable in their region. And there is a Latin American subcommission, a China North Asian subcommission, and a Southeast Asian subcommission. And today, this is a good example of such work of an Icmsf subcommission, since the Latin American subcommission is organizing this webinar, and it are mainly Marta Tanaraki and Bernadette Franco that have been facilitating this session, but together with the whole Latin American subcommission team has been working on this webinar. Already last year, we also had a webinar with a cooperation between the Latin American subcommission and the Icmsf. And that was also around this period. It was then from 13 to 15 of April. And that was a great success. We had a lot of participants from all over the world. Also, many people presenting, both from the Icmsf and from the Latin American subcommission. Also, all the videos were recorded and put on YouTube. And therefore, we thought this was a great success. And therefore, we decided to continue it this year with a second webinar. So the Icmsf is also producing books, and we have been producing books since the 1960s, when the Commission started, about microorganisms in food and methods of enumeration, things about HACCP, about all kinds of food safety management. Initially, we were focusing on methods and testing, then more on microbial ecology and HACCP, and our latest books are related to risk management. And the book that we are working on now is book 9, Managing Food Safety and Stability in the Context of the Global Megatrends. This we are still working on, so this is not an official book that did already come out. Again, the subcommissions are very strong in disseminating this material, because all these books are also translated in Portuguese, in Spanish, and in Japanese, and in Chinese. And also it is often presented in workshops and conferences all over the world, organized by these subcommissions together with members from the Icmsf. Last year, we commemorated 3 members, both from the Latin American subcommission and also from the commission, that unfortunately deceased. Ricardo Sobol deceased 2 years ago, Hans-Jürgen Schnell and Russ Flowers. But unfortunately also this year, we have to commemorate one of the members of the Icmsf, and that is John Pitt. He unfortunately deceased the 23rd of March this year, so a couple of weeks ago. And John was a very well-known mycologist and expert in food fungi, and he was an Icmsf member and consultant between 1987 and 2003. Apart from doing his work at the Icmsf, that was only a small part of his work, but he contributed a lot to the committee. He also worked at the CSIRO in Australia, and he worked there from 1954 to 2019. So a lot of people retire when they are 65 years old, but John did retire after 65 years of service. So he worked there for 65 years, and from 2002 onwards as an honorary research fellow. Also, John worked a lot together with the Latin American subcommission, and particularly with Marta. And together with Marta, I looked that up in the last 20 years. he did produce 18 papers where they were both co-authors, all related to fungi and in many cases on mycotoxins. And many of these papers also got a very strong attention and got a lot of citations. So this was really a great symbiosis between John and Marta and between the Icmsf and the Latin American Subcommission. So today we are going on the webinar on diving deeper into the Icmsf approach to microbiological food safety management now and in the future. There are 3 days. The session will take 4 hours, and this is the first day. And tomorrow it will be a similar day where we have first knowledge clips that we discuss, and we have questions and answers on them. And after that, there are presentations from Icmsf members. And the April 26th, so in 2 days' time, there will be roundtable discussions that are all interactive. So the third day will be a little bit of different setup. So the first day will be about utility and microbiological sampling and testing. That will be video clips and interactive virtual live question and answers. And after the coffee break, we will go to presentations on developments in risk-based food safety management. And there will be virtual live presentations. So they are virtual, they are on distance, but they are live presented. And there is an interactive virtual live question and answering. And for that, you can send questions to us from the YouTube platform. So the second day, it will again continue with microbiological criteria and underlying statistics with video clips and Q&A. And then there will be live virtual presentations on application on sampling and testing principles applied to different commodities. And like mentioned, the third day, there will be roundtable discussions about opportunities and challenges to current and future risk-based food safety management, utility of microbiological criteria and useful testing approaches, and managing Listeria monocytogenes in time of peace and in time of crisis. And for all these 3 sessions, also you can already beforehand send in questions, because the panels will discuss these subjects, but also we would much rather have questions that are posed by the participants at that moment. But it would also be handy if already you have questions on these subjects that you already submit that to us so that we can prepare some answers. So today we have started with the opening and the introduction of the video clips by me, and we are now one by one going to look at these video clips and give a short introduction. Then you watch the video clips, and then there will be take-home messages that we distill. And after all the video clips, there will be question and answering and discussion on the video clips. And please send us questions that you already have specifically on these video clips while they are running, so that we can prepare for answering the questions. But also, of course, during this question time, at that moment, you can also post your questions. So the video clips that we do show you are in total 8 video clips that are a selection from all the video clips that have been produced by the Icmsf. There are in total at the moment 19 video clips produced that you can all find on our website. But we will now show and discuss 8 of these video clips. So today we have 430 inscriptions for YouTube, and there are about 30 people that are connected to Zoom, because when we are presenting and answering questions and so on, we are in another platform that is connected to your YouTube, and we are with 30 members from the Icmsf and from the Latin American Subcommission in Zoom. So in total, there are about 460 potential participants for these 3 days. And we are from 32 different countries. There are participants from 21 different countries. The majority is from Latin America. There are 14 because that is really the organization part. But there are also people from Europe, Asia, North America, Oceania, Middle East. And there are 20 people from countries that are not related to one of the speakers, but there are 11 different speakers from 11 different countries. So I now give the floor to Leon, who will continue and start to introduce the first video clip.
Thank you very much, Marcel. Also from my side, welcome to all the participants to this webinar. For the first session today, we have selected 4 of the video clips that Marcel introduced. We have 19 video clips on very many different aspects of useful testing in food safety management and in food safety assurance. And we selected 4 that give you a number of key concepts and pieces of information on microbiological testing. The first video clip will be presented now we go too far. The first video clip will be presented by Dr. Bob Buchanan. Dr. Bob Buchanan is Emeritus Professor at the University of Maryland in the US. And Bob has been a member of the Icmsf for 20 years and a consultant for the Commission for another 10 years. The title of Bob's presentation is Microbiological Testing Basics. So he will look at what kind of tests there are for microbiological investigation, what the purpose of those tests is in food safety management, and he will emphasize that testing really is a probabilistic undertaking that you really have to understand well. So over to the first video clip. Thiago, could you start it, please?
Hello, I'm Bob Buchanan, Professor of Food Safety at the University of Maryland and a retired member of the Icmsf. This presentation is about the role of microbiological testing in ensuring the safety and quality of foods and food ingredients. In this presentation, you will be introduced to some of the concepts upon which microbiological testing is based and how such testing can be used effectively to develop and implement food safety management programs. The microbiological examination of foods and food ingredients against a specified criterion is one of the common tools used to assess the effectiveness of risk management programs for ensuring the microbiological safety and quality of foods. Despite the wide use of microbiological testing, there is a limited understanding among consumers and even among many food professionals about the principles and concepts underlying testing. The purpose of the current presentation is to introduce several important testing concepts that will be subsequently expanded in other modules. The microbiological testing of foods is a family of different types of tests that are designed to acquire knowledge needed for decisions related to the microbiological suitability of foods and food processes. Thus, they represent a toolbox of technologically based and statistically based tools that provide specific types of information. This includes acquiring information on the safety of individual lots, validating the effectiveness of food control systems, and verifying that these systems are operating as intended. Furthermore, microbiological testing is used extensively to investigate the loss of effective control of quality of incoming ingredients, the loss of process control, breakdown of distribution and marketing systems, and how foods are being used or even misused by the ultimate consumer. This can include targeted investigational sampling or more generalized surveillance to assess the status of the food industry segments. This is one of the most important roles of food safety microbiologists is picking the right tool for the right job. One of the keys to understanding microbiological testing is we are dealing with probabilistic events. When dealing with a pathogenic microorganism, one is typically dealing with low levels of contamination. This means that it is possible that the target microorganism might not be found in specific samples being examined. Considering that microbiological testing is a destructive process, the only way we ensure absolute absence of a microorganism of concern would be to test all of the food, leaving none left for the consumer. Thus, if one is testing only a portion of a food lot, one cannot absolutely prove the absence of a pathogenic microorganism. However, negative findings are useful. They indicate that the microorganism of concern is present at a level below that which the sampling plan is designed to determine. It also provides a means of estimating the level of confidence that one can have that the target microorganism is truly absent. As previously mentioned, microbiological testing is a set of statistically based tools. To fully understand and correctly interpret the results of testing programs, one must be aware of the statistical foundation upon which the testing is based. For instance, statistical basis for testing assumes that the samples are taken randomly and independently. If this assumption is not met, then an alternative statistical analysis or sampling schemes may be required. It's also worth noting that one of the challenges in sampling foods is actually taking a random sample. Another important concept in determining the sensitivity of a microbiological testing program is understanding defect rates. Put simply, the defect rate is the percentage of food servings that contain one or more cells of the microorganism of concern. The more servings in a food batch that is contaminated, the more likely it is that we'll select a contaminated serving for sampling. Conversely, if the defect rate is low, for example, less than 2%, selecting a contaminated serving may be the limiting factor in detecting a contaminated batch. There are two general types of sampling plans used in microbiological testing of foods: variables and attribute testing. Variables testing involves the direct use of quantitative data and is seldom used in food testing programs. Instead, food testing almost exclusively uses attribute testing. This type of testing stratifies the testing results into acceptable and non-acceptable attributes. In two-class attribute testing, the responses can be based on a simple presence and absence testing, which is often used in assays that are focused on the identification of pathogenic bacteria. For example, sampling plans for Salmonella or enterohemorrhagic E. coli are based on simple detection of the microorganism and not on the levels present. The second type of two-class attribute sampling plans involve the use of quantitative data that have been stratified into acceptable and non-acceptable levels. This is often used in conjunction with indicator microorganisms such as coliforms, generic E. coli, or mesophilic aerobic plate counts. In addition to two-class attribute sampling plans, three-class attribute plans provide certain advantages when working with stratified quantitative data. In three-class plans, a third marginally acceptable class is defined. In this approach, if all the samples have a level of the target microorganism that is acceptable, this number is often referred to as little m, the food batch is considered acceptable. At the other extreme is a class where if any sample exceeds a specified upper limit, often referred to as big M, the entire batch is considered unacceptable. In between, greater than little m and less than big M, is the marginally acceptable class. In this instance, if the number of samples in this range are less than a specified percentage of the total number of samples, the batch is considered acceptable. Conversely, if the number of marginally acceptable samples exceed that specified percentage, the batch is considered unacceptable. The characteristics and examples of the various types of sampling plans will be considered in more detail in later modules. One of the key attributes of microbiological testing program is establishing how stringent the program needs to be in terms of the likelihood that a target microorganism will be detected. This can be a highly complex decision since the degree of stringency is based on a variety of parameters, such as why is the testing being performed, the cost of the analysis, the expected defect rate, the distribution of contamination, the number and size of samples, the frequency of sampling, the lower limit of detection of the testing method, and finally, the degree of statistical confidence required. Food production, processing, distribution, and marketing often involve complex supply chains that often include both the international sourcing of ingredients and the international distribution of products. Thus, a key question in microbiological testing is where along the food chain should one sample? Two key attributes influence the type of samples to take and where to take them. First, contamination typically flows with the food manufacturing process. Second, microbiological testing results at a specified point in the process reflects the impact of all the manufacturing steps prior to the sampling point. Thus, if an ingredient is sampled upon receipt, the results reflect the control steps by the supplier and other additional changes that occurred during transport. Likewise, an inline sample reflects the sum of all the factors that influence the product's status up to that point in the processing. Sampling at the end of manufacturing is conceptually the same. It is the integrated sum of all the factors that impact the microbiological status of the product, from receipt of ingredients to final packaging. However, most manufacturers view end product samples differently. This reflects the fact that this is generally the point in manufacturing where the food comes under regulatory control. Most scientists learn about analytical testing as part of their training in chemistry. This includes learning about lower limits of detection that involve achieving a certain signal above background noise level, characteristic of the method. The same is true in microbiology, where increasing the signal is achieved through the use of selective media, genomic-based methods, or immunologic methods. However, microbiological testing is different from chemical testing because we are dealing with particles, not molecules. This means that at low levels, one has to be concerned about whether the analytical unit being tested actually contains the microorganism. This is becoming increasingly important as microbiological testings move to smaller and smaller sized analytical units. It is also important to note that this concerns both traditional cultural methods and new genomic and immunologic rapid methods. When dealing with the particulate nature of bacteria, the size of the analytical unit being tested becomes the key determinant of the sensitivity of the method. For every 10-fold decrease in the size of the tested sample, there needs to be a 10-fold increase in the concentration of the target microorganism to achieve a high level of confidence. Thus, if you're testing a 0.1 milliliter sample of food that has the mean concentration you need is about 200 cells per milliliter, as opposed to if you're testing 1 microliter, you need to get a concentration of about 20,000 cells per milliliter. When dealing with food samples that contain the target organism at mean log concentrations below those needed for a high degree of confidence of detection, analytical methods may need to be modified to reach the desired level of sensitivity. Two ways of doing this is to increase the size of the analytical unit, say from 1 gram to 25 grams, or to increase the number of analytical units being examined. This can also be combined with either concentrating the sample or enriching the sample. Concentration is commonly used in the analysis of water or other liquids, where a relatively large volume of liquid is passed through a micropore filter, which allows the water to pass through but retains the bacteria. The filter can then be transferred to microbiological plates and colonies allowed to develop. For enrichment, we take advantage of the ability of bacteria to replicate in a suitable liquid medium. The analytical units, either individually or as a composite, are transferred to the enrichment broth and allowed to grow under standardized conditions. At the end of the incubation period, the target microorganism should have grown sufficiently to be readily detectable. The key to successful enrichment is incubating the samples for a sufficiently long period to allow attaining the target population levels. For example, the lower picture depicts a 2-liter enrichment of 15 10-gram analytical units. If only one of those 15 samples contains the target microorganism, the enrichment is going to have to support the growth of the microorganism from 1 cell per 2,000 milliliters to 20,000 cells per milliliter, if you were going to use a 1 microliter aliquot to subsequently test. In summary, various forms of microbiological testing are routinely used as part of the systems to ensure the safety of foods and food processes. The tools are technologically based and statistically based, and we need to understand the factors that influence such testing that makes effective testing and interpreting the results useful. This includes factors such as lower limits of detection, sample size, and the other factors I have previously mentioned in this talk. This video introduces several of these factors and concepts. Subsequent videos will explore these factors in much more detail. In addition, the Icmsf provides different reference books that explore this material in detail, and we particularly recommend that you review the material in ICMS book, Microorganisms Food, Book 7 and 8. The former provides the scientific principles underlying microbiological testing, and the latter provides examples of how these tools can be used in food safety management programs. In addition, ICMSF also makes available a series of free tools that can be downloaded from the ICMSF website.
So that was Bob's introduction to the basics of microbiological testing. Very important point that Bob is making. Although testing in the context of food safety certainly contributes to food safety assurance, you can't just use testing, not testing only, because then there's nothing left to sell, to give to the consumer, because you really have to test every item to make sure that there are no microorganisms that would cause a risk. And it is important to understand that indeed testing itself is a probabilistic event. It depends on chance, the chance of an organism being present in a sample taken, the chance of an organism being at a detectable level in that sample, and the knowledge of microorganisms, their ecology, their physiology in food and in food operations is very important to have because that gives an understanding of the probabilities. We also have to understand the test method, the sampling method, because that relates to the sensitivity of testing, and both probability and sensitivity in that regard are key elements when you want to select the right tool for the job, as also Bob called it. So let's go to the next video clip, which will be introduced by Marcel.
So the next video will be given by Katie Swanson, and it's about microbiological testing for validation and verification. And like the title already says, the main message in this video clip is to explain clearly the difference between validation and verification. So Tiago, can you please start the video with Katie?
I am Catherine Swanson, Icmsf member since 2001 and food safety consultant. This presentation is about microbiological testing for validation and verification in food processing. In this presentation, you will learn the difference between verification and validation and why both are important for an effective food safety management program. The term microbiological testing brings a variety of images to mind depending upon the audience and the individual. For example, some people think about vast quantities of data that can be analyzed for risk assessment. Others think of using microbiological testing in a detective game to identify an unknown microorganism or a causative agent in a foodborne illness outbreak or spoilage situation. Still others think of microbiological testing as an implied guarantee that a specific lot of food is absolutely safe without recognizing that uncertainty exists. And others, microbiological testing is a practical quality management tool that provides information to indicate whether a process is performing as expected. Different types of testing can be applied for all of these purposes. However, this presentation focuses on the last two elements, that is, testing for process control and product acceptance. For effective food safety management, it is important to consider both validation and verification. Let's start with validation first. According to the Codex Alimentarius Commission, the term validation means obtaining evidence that a control measure or combination of control measures, if properly implemented, is capable of controlling the hazard to a specified outcome. In other words, proper validation answers the question, does the control actually work? To determine this, scientists and engineers conduct studies, such as cooking to a certain temperature and for a certain time, to obtain evidence a process or treatment will reliably destroy specific pathogens of concern. As the temperature of a product increases with time, the initially happy bacteria become stressed and are ultimately inactivated to a specified outcome in a properly validated process. The specific treatment varies depending upon the process, the food, and a number of other factors. Because of this, proper validation is essential to determine critical factors that ensure a food safety plan can actually control the identified hazard. Without proper validation, the effectiveness of the process to control food safety risk isn't known. Regulatory guidance or industry standards frequently provide validated process parameters for many products. For example, time and temperature requirements for pasteurized milk are typically specified by governments. When such guidance is not available, proper validation is important to avoid taking bad road and having a food safety incident because the designed process is not effective at actually controlling the hazard. There is an obvious link between verification and validation. Codex Alimentarius guidelines define verification as the application of methods, procedures, tests, and other evaluations in addition to monitoring to determine whether a control measure is or has been operating as intended. While the process validation study provides evidence that the process will control an identified hazard, it usually assumes that good hygienic practices are implemented, equipment is capable of delivering the process, and employees are trained to perform their assigned task properly. Verification is needed to provide evidence that these conditions are met. Many verification procedures do not involve microbiological sampling and testing. However, it is important to recognize that such testing may be useful for some products. This may include targeted sampling and testing of ingredients, in-process materials, environmental samples, and finished products. Recommended microbiological tests can vary considerably for different food products. There is no specific set of tests that are useful for all food products. However, Icmsf's Microorganisms in Foods 8 use of data for assessing process control and product acceptance, which is published by Springer, identifies microbiological testing for 19 different food product categories. These tests may be performed on samples from primary production, ingredients, in-process samples, environmental monitoring, shelf life tests, and end products. Introductory chapters also address general principles related to microbiological testing of food, including validation of control measures, verification of process and environmental control, corrective action to reestablish control, and microbiological testing in customer-supplier relationships. You can find information on this book on the publisher's website, and translations of Book 8 are also available in Spanish, Portuguese, Chinese, and Japanese. In 2018, the second edition of Microorganisms in Food 7 is anticipated, and Book 7 provides more information on validation and verification. In conclusion, recommended microbiological tests can vary considerably for different food products. Despite limitations related to the sensitivity and time to result, microbiological testing can play an important role in effective food safety management. For many products, validation testing is done to determine the specific parameters that, when properly controlled, will effectively control the microbial hazard of concern. Verification testing is also recommended for many food products to demonstrate that controls are being implemented as intended. Please visit the Icmsf website at www.icmsf.org for more information on Icmsf books and tools.
Okay, so you have seen now the video of Catherine Swanson, and I would like to remind you that you can already post questions. There is on the YouTube also a possibility to post questions. Please do so. Then the Icmsf members can already have a look at the questions that are posted, and they will arrive on our screens. So the take-home messages from this last video is that there are two important things: validation and verification. Validation you do before the start of the food operation, and the verification you do during the operation. So validation you do before, and with that you show that the control measure in principle would work. For instance, that heating at 72 degrees at 15 seconds gives in your food product a sufficient reduction. So that is a validation. So it's before you start operating, you show that with certain conditions you reach a certain objective. Then during operation, you are going to verify if things go really as intended. And one of the things, for instance, what is called verification, is that you actually check that the temperature is 72 degrees and that the residence time is 15 seconds. Also, maybe you see on your thermometer that the temperature is 72 degrees, but it's good to calibrate your thermometer and to really see if it is correct. So that is all kind of verification. Another step of verification is, for instance, that in the end product, you are going to take samples to see that salmonella is not detected in 5 samples of 25 grams. That is also during operation that you verify that things are going as intended. So I now give the floor to Leon to introduce the next video.
And the next video also has been recorded by Katie Swanson. And in this one, Katie focuses on process control during operation, with the testing being used for verification of the proper control of that operation, and also using verification data to analyze trends in process control. And thank you, Thiago, for starting that video clip.
I'm Catherine Swanson, Icmsf member since 2001 and food safety consultant. In this presentation, I will discuss the use of microbiological testing for verification of food processing control. Quantitative tests for indicators or presence-absence testing for pathogens could be used. Which do you think is more useful to manage an effective food safety management program? Let's take a look at an example. When a manufacturer makes a food product, they know the specific processing conditions used. Proper validation of the food process provides greater assurance of food safety. Verification testing under processing conditions can provide information over time to demonstrate that the validated process is implemented as intended. In this hypothetical example, common ingredients are used for 3 different processes. Process 1 makes product for packaging line A, while the products from processes 2 and 3 are packaged on line B. The company conducts verification testing on each of these 2 packaging lines to monitor trends between lots and demonstrate that the processes are performing as expected. Remember that the same ingredients are used on all lines. What action do you take when an unacceptable result is found on line B? This chart illustrates hypothetical data for packaging line B using presence-absence testing for a pathogen. Keep in mind the product continues before the results are the production continues before the results are known because testing takes time. A pathogen is detected in lot number 8. As other Icmsf videos illustrate, it is difficult to know whether lots with a negative result may have low-level contamination that was not detected because of the sensitivity of microbiological testing. Thus, a positive result for a pathogen calls into question the safety of the lots produced before and after this positive lot. This chart also indicates or illustrates hypothetical data for packaging line B. However, a quantitative indicator is used. Many times, quantitative testing provides more actionable information for verification purposes. In this example, the line indicates a hypothetical maximum acceptable level for the indicator. When the data indicate that lot 8 exceed the acceptable levels, other lots are well within the acceptable range. This example provides assurance that conditions present support safe production of food, while the company takes action to determine the root cause of the unacceptable result for lot 8. This is an example of the usefulness of microbial testing for between lot verification. While quantitative microbiological testing does not provide real-time results for immediate action, it can be very useful when trend analysis is conducted. This requires examination of the data between lots. This example illustrates an increasing trend. It may indicate growth of bacteria in the processing line and perhaps the need for sanitation of the lines. This chart illustrates the benefit of charting the information in a timely manner to avoid exceeding limits. A company may have initiated investigation earlier to determine the cause of the fairly constant increase before unacceptable levels were observed. Some processes have significant variability, as illustrated in this chart. For example, variation can be observed in raw produce when weather patterns change. Seasonal variation can also be observed. A minimum of 30 lots of production is recommended to establish a baseline, but more data can be necessary to account for seasonality. This example illustrates a substantial difference in performance, which should be investigated. Is it due to seasonal variation? Was there a new ingredient used? Are new employees working? Is the process malfunctioning? Are pathogens detected through other testing? Using both quantitative indicators and presence-absence pathogen testing can be useful to evaluate situations such as this. Statistical process control can be a very useful tool in evaluating verification data for process control. When using microbial count data, the lower confidence limit, CL, typically is not considered to play a role, but automated statistical process programs will provide the information anyway. The upper control limit indicates a loss of control. Notice that the loss of control occurred around week 50 and 51, which would require investigation and likely corrective action. A proper verification activity would have included review of the data to observe for trends. For example, an increasing trend began in week 42 and continued with a few reductions up to loss of control at week 50. It is strongly encouraged that verification data for process control be evaluated for trends to enable corrections before loss of control. In conclusion, routine microbiological testing for verification can be highly beneficial when analyzed between lots for trends. Routine microbiological verification testing can provide assurance that conditions enable safe food production, the basis for analyzing performance trends so that corrective action can be taken before loss of control, insights into the cause of loss of control, and a warning that conditions changed, which may indicate the need to review and potentially revise the plan. Icmsf's Book 8 provides microbiological testing recommendations for 19 food product types. Please visit the Icmsf website for the latest information on Icmsf books and publications.
So following up from Katie's presentation, some take-home messages and thoughts, and maybe the first one should be about maybe microbiological testing is not the only tool we have for verification of product and process control. It's a very important one, but more often than not, we use physical testing or testing of chemical parameters. But there is a place for routine testing of microorganisms in foods or in the processing environment for verification of process control. We can look at pathogens, we can look at non-pathogens for that. Pathogens typically occur at very low levels. They are at low levels that need qualitative detection methods, and that doesn't give you a lot of information. The fact that non-pathogens occur more frequently in food at the higher levels, you can quantify them, you can see trends in their occurrence, helps in a way to do the verification testing, but also allows for trend analysis. With that, we go to our last video clip in this session, and it will be introduced by Marcel.
The next video clip will be presented by Leon, so I will introduce this video clip, and that is about the Icmsf cases concept. And the Icmsf approach is meant to give useful statistical testing for food safety assurance. And this food safety assurance is both really focused on food safety, so on pathogens, but it can also be on non-pathogens, more related to general indicators or quality. So please, Thiago, can you start the next video?
My name is Leon Goris. I am Global Regulatory Affairs Director of Unilever, with responsibility for food safety. I have been a member of the International Commission on Microbiological Specifications for Food since 2001. As one of my contributions to Icmsf, I represent the Commission at Codex Alimentarius, the global body that develops food standards, including those related to food safety. In this module, I will provide you with an introduction to the cases concept of the Commission. That was first published in Book 2 of the Microorganisms in Food series. This book was published in 1974 and updated in 1986. Our concept recommends 15 cases that may be used to determine the microbiological safety and suitability of foods in trade or coming onto markets, especially when there's no other information available. This typically would be the case in a port of entry situation where a food shipment may arrive without proper documentation of product safety or suitability. The Icmsf cases concept is an example of risk-based food safety testing, as it matches the testing stringency of sampling plants in proportion to the consumer risk posed by different microorganisms possibly occurring in food. The concept has been applied by many organizations around the world, including Codex Alimentarius, governments, and industries. The Icmsf established the cases concept on the rationale that the greater the risk to the consumer is, the more stringent the management of the hazard involved needs to be. The level of consumer risk is related to the type and number of a microorganism present in the food when it is eaten. Generally, consumer risk is increased for a given microorganism when it has grown to high numbers. Conversely, the risk is usually reduced if the number is reduced. In the concept, a greater consumer risk is reflected by a higher case number, while the testing stringency of the sampling plants recommended have been selected such that their performance increases proportionally with the increased level of consumer risk. In our cases concept, we differentiate 15 cases that reflect the relative risk to consumers by combining 3 key considerations. The first is that the harmfulness and severity can differ between microorganisms. Indeed, some microorganisms may be harmless and have no impact on the health of the consumer. Others may be a hazard and cause harm or illness. The degree of harm or illness depends in part on the severity of a particular hazard. It also depends on the vulnerability of the consumer to fall ill after having ingested a pathogen with the food that they eat. when the intended consumer population is generally healthy, their vulnerability may be much less than that of very young or elderly consumers. Finally, the risk to consumers also depends on the conditions of handling and use of a food after it has been produced or manufactured. Some foods are held under conditions that allow microorganisms to grow, while other conditions reduce or maybe even stop the growth of microorganisms. For instance, when food is held under refrigeration. Also, the final preparation and consumer use of a food may affect the levels of microorganisms in food, with an example being that cooking before consumption generally will reduce numbers of microorganisms. The 15 Icmsf cases have been categorized in a matrix in which these three conditions and considerations are included. From top to bottom, we categorize the impact of the types of microorganisms. Moving down from row 1 to 5, we move from microorganisms with no health impact to those with a severe health impact. Going through the matrix from left to right, 3 different conditions of handling and use that affect the levels of microorganisms are reflected in the columns A to C. Overall in the matrix, going from A1 to C5 reflects going from the lowest to the highest level of consumer risk posed by different types of microorganisms and conditions. Now let's first have a look at the types of microorganisms that we consider to fall in the 5 different categories. We start with the category of utility organisms. These generally do not cause illness, but may, for instance, be related to the spoilage of food or to shelf life reduction. Example, microorganisms that fall within this category are total colony counts, as well as yeast and mold counts. The second category is that of indicator organisms, which relate to organisms such as Enterobacteriaceae that may be used to evaluate adherence to good hygienic practices. Also, indicator organisms themselves generally pose no health concern to consumers. Various potential pathogens are now grouped in 3 different categories. First of all, we have the moderate hazards, like Staphylococcus aureus, Bacillus cereus. These generally cause only mild and self-limiting illnesses. Next, we consider serious hazards, such as Salmonella, which are incapacitating, but mostly are not life-threatening. The last category is that of severe hazards, and includes those microorganisms that can be life-threatening and are associated with chronic sequelae. This is also the category for pathogens possibly occurring in foods intended for sensitive subpopulations, such as infants, elderly, or those with underlying medical conditions. Examples of severe hazards for the general population are E. coli, O157, and Clostridium botulinum. Another example in this category is Chronobacter, occurring in infant formula, which is of specific concern to very young infants. Let's now look at how the categorization of microorganisms is combined with proportional testing stringency in order to determine whether a certain food lot is acceptable. When we talk about accepting food in trade or food coming onto market, we mostly consider batches of food that are referred to as food lots. A food lot is a specified quantity of a food that has been produced or manufactured under uniform conditions. Depending on, for instance, ingredients, production, and processing methods used, food lots may contain different microorganisms and they can occur at different levels. To determine whether a food lot is acceptable or not, the Commission suggests to use a sampling plant for testing, of which the performance is proportional to the relative risk to consumers. In the cases concept, the Commission uses 2 types of sampling plants, namely 2-class plants and 3-class plants. 3-class sampling plants differentiate between 3 classes of sample results: acceptable, marginally acceptable, or non-acceptable results, while 2-class sampling plants differentiate acceptable from unacceptable sampling result. The parameter N that is used in both sampling plant types stands for the number of sample units to be taken from a lot. The parameter small m and the big M specify the microbiological limits. parameter C is the maximum allowable number of sample units that can be over the relevant limit for a food lot to be acceptable. Now let's put the categorization of microorganisms together with the sampling plans for lot acceptance. With 5 categories of microorganisms and 3 conditions, there are 15 cases that reflect different levels of possible consumer risk. From top to bottom, we have the categories of microorganisms listed. From left to right, we consider different conditions that impact on the level of a microorganism. Column A reflects conditions that potentially reduce the number. Column B, conditions that do not change the number of a microorganism, while column C is for conditions that possibly allow a microorganism to increase in number. For utility and indicator organisms, as well as for moderate pathogens, 3-class sampling plans are proposed. These involve quantitative tests that enumerate the microorganism, so test results are expressed as CFU per gram. For serious and severe pathogens, 2-class plans are suggested in combination with presence-absence tests and analytical units of 25 gram. The sampling plan type, together with the values chosen for various parameters, determine the performance of a sampling plan. Here we have an overview of the matrix, with the sampling plans and parameters N and C indicated for cases 1 through to 9, for which 3 class plans are used. As can be seen, the parameters N and C differ for the 3 conditions indicated in the columns. By reducing the number of C for the same number of N, going from conditions that reduce to those increasing microorganism level, sampling plans become more stringent. This is the case when comparing cases 1 to 3 for utility microorganisms, or when comparing cases 4 to 6 for indicator organisms. For the moderate pathogens, stringency is increased by reducing C between cases 7 and 8, or by increasing N between cases 8 and 9. As an example, case 8 would apply to a moderate pathogen, such as Bacillus cereus, that will not change between the time of sampling and the time of consumption. While in case 9, this pathogen could increase in numbers before consumption. Regarding the serious and severe pathogens, for which 2 class plans are used, the same principle applies, with N being increased now from 5 to 20 for cases 10 to 12, and from 15 to 60 for cases 13 to 15. In all instances, C is 0, which means that not a single of the recommended number of sample units should yield a positive result for the pathogen in order for the food lot to be accepted. As an example for this, to accept a food designed for a sensitive subpopulation, such as a lot of infant formula, one could consider that Salmonella is able to quickly increase in numbers at the consumption phase. This can happen, for instance, when the powdered infant formula is inadequately reconstituted when a caretaker prepares a feeding bottle for an infant. In this case, the sampling plan of case 15 would be appropriate, meaning that 60 sample units of 25 grams need to be analyzed of the infant formula lot, and that this lot can only be accepted when none of the samples is found to be positive for Salmonella. In summary, the Icmsf cases concept has been established as a systematic approach to manage microorganisms in food according to the risk that they pose to consumers. The greater the risk, the more stringent is the sampling plan recommended for testing. While the concept has been launched by the Icmsf some 40 years ago, the Commission is still updating and extending its scientific and technical advice on sampling plans and on other useful testing approaches. Our most recent thinking is provided in books 6 and 8, which are available in several languages. Please also consult our website for further information.
Okay, Leon has explained the Icmsf cases concept, and he has clearly shown that at a greater risk, more stringent control needs to be taken. And the risk can be greater if the pathogen becomes more severe, that is one side, and the other side is if the pathogen either will decrease or remain stable or increase. So then also the risk goes up by the presence of the pathogen or by the severity of the pathogen itself. The Icmsf risk category basis control also has statistical implications, and the more samples you take and the lower the value of the C, the better control you have, and have a statistical influence on the lot acceptance. And the concept can be applied for all kinds of food commodities and along the whole food supply chain, next to targeted environmental sampling and process control. End product control is relevant and important to do, but also next to it, environmental control is needed. There is not one silver bullet that can solve all your issues. It's often a combination of all kinds of different aspects. So this was the fourth video that we did show with a short introduction and some digestion of the messages that we can get out. And we are now going to the next part of the session, and that is the questions and answers. And so we are now at the question and answer stage and discussion on these subjects. And for that, you can still post questions, so please do so. There is the possibility to post questions on YouTube, then we will see these questions. There are already 2 questions posted that we can respond to, but we would like to urge you also to start posting questions both on these YouTubes that we have just discussed, but also maybe later today or later tomorrow for the roundtables that we do on April the 28th, because on these subjects, it's also good that some questions are already posted beforehand, and they are on the same aspects. It's on microbiological criteria, on food safety management, and specifically on listeria control. So please also look at the subjects for April 28th and already post questions for that. Please then also mention the number of the session that you are referring to. But I will now go to the first question, and both Leon and me will answer these questions, but also other members of the Icmsf or members from the Latin American Subcommission that are here present in the Zoom link can also, of course, intervene and mention that they want to respond to a certain question or take the floor, or also maybe want to ask a question. That's all possible. But the first question I will read out. And that is that if there is one Listeria monocytogenes sample in a ready-to-eat food product, is that now enough to stop processing plants without any other evaluations? So we find in a ready-to-eat meat production facility, we find, for instance, the sampling plan is 5 samples. If one is then positive, do we have to directly stop the processing plant and do a recall without any other evaluation? There is not one black and white answer that we can directly say yes or no. It is like most often, there is more to say about it. And also the presentations of tomorrow and the day after tomorrow will continue in that. So please, Maria Teresa, where the question came from, post it again, maybe at the last day. Then we'll give now our first reflection on it, but later on we'll give more information. So the first thing, and the response to the question is, it depends where on the world you are, because in the United States, Listeria monocytogenes is seen as an adulterant. If there is one sample positive, it's always not complying with the law. And indeed, it's like you state, it has to stop processing and the product has to be taken off the market. In, for instance, the European legislation and in many other regions of the world, it depends if the food product supports the growth of Listeria or does not support the growth of Listeria. So if this is a growth supporting product, also in Europe, it would be seen as a not compliant batch, and it has to be taken off the market. In case it is a non-growth product, it depends if the level is above 100 CFU per gram or not. Also in the European legislation, there is even an additional derogation saying that if you find the positive, but if you can prove that within the shelf life of the food product, the level will not reach 100 CFU per gram, still you don't have to take it off the market. So you say, does it have to be taken out of the market without any other evaluation? If you have beforehand shown that if there is a certain level and with the composition of your food product, the growth of the organism is very minimal and it will not reach 100 CFU per gram during the shelf life, if you have a good dossier to support that, still it can comply with the European legislation. But like what Leon showed in the presentation with the cases also, it depends of course on the growth and the no growth, that is one side, but also on the severity of the organism and the population group. If for instance this food product would be intended for infants or for babies or for instance hospitals, again this would be, I would consider this, even if it's a non-growth food product, I would consider this not as okay to send to the market. So it depends. Is it growth or no growth? It depends also on the region of the world that you are, and it depends also on the target group of the food products. Maybe Leon wants to add an additional thing to this answer, or maybe some other members.
Oh, I think, Marcel, you covered all the aspects of risk that we would consider in evaluating what to do with a positive sample in a processing plant. Of course, we would, let's say, try to avoid having listeria in food processing plants. And in that regard, environmental testing in those plants is relevant. Finding organisms when they are there is important, especially if they would be hiding in equipment and other places. So there's a lot of effort being done to find organisms and to clean, let's say, the operational environment very much. And in that process, you could find, of course, listeria in a plant, maybe not in the end product, but in the plant already there. Of course, there could be a concern from the regulatory point of view in certain jurisdictions, as Marcel explained, but in terms of risk, some jurisdictions would take different measures, put up different standards regarding listeria in ready-to-eat food.
There was a second question related to salmonella, and in Peru, the legal standard says for salmonella absence in 60 samples of 25 grams, but it also says that you can mix these 60 samples and then take 5 samples of that and analyze that. And the question is, what is our opinion on that legislation? Again, it depends on where we are in the world. The Codex says 60 samples of 25 grams for salmonella in powdered infant formula. So realize that this is for a specific food product for a very sensitive group of population. If this would be salmonella in meat or salmonella in chocolates, there would be often 5 samples of 25 grams. But specifically for powdered infant formula, Codex says 60 samples. In the EU legislation, for instance, it says 30 samples of 25 grams. However, it is not allowed to then subsample like what is in the legislation in Peru. So if you have 60 samples and then 25 gram portions, and then only analyze 125 grams of that, then you have a much less sensitivity, of course, than if you would take 60 samples of 25 grams. So I'm not a manager. It's, of course, like what is mentioned in the question, the more analysis you have to do, the more costly it is. Indeed, that is the case. But on the other hand, we are dealing here with a very sensitive population group, and we have just had a big outbreak in the United States, again with salmonella and powdered infant formula, and we have had also an outbreak a couple of years ago in France and in Spain on this in this specific product group. So we should not be too lenient in our criteria. So 60 samples of 25 grams is quite sensitive, but still you can miss contaminations. Only analyzing 5 samples might be a little bit too lenient, in my opinion, but it's always often a balance between costs and the residual risk that you will have. Leon, any additions?
Maybe one addition is that even if there are different kind of standards requiring different numbers of samples to be taken, maybe there are standards that take samples of 10 gram portions, not 25. but those different standards exist. If you would like to compare what the performance of those standards would be, the Icmsf sampling plant tool could be used to see what is the difference in the number of samples you take in the level of organism you can detect. And I think that might help also in the decision on what number of samples to take, but also if you would like to, if you would consider subsampling or mixing, what the performance would do in that regard. But we come back to that tomorrow morning in session 3.
And there is also a question on how to take into consideration the size of the lot when using the 15 categories of the sampling plan. Yeah, for that, we are very black and white as Icmsf. We always consider doesn't matter what the size of your lot is, you define what the size of your lot is, and for that, then you use your the 15 cases. If you decide that you take a whole week production as one lot and you produce that without cleaning and just continuously, and it's all using the same ingredients and so on, that is then one lot. It's a very big lot. You still need to take the amount of samples that are given in the tables. If then you find a positive, the result is also that you have to reject then that whole lot. So the sampling is then maybe cheaper, but if something goes wrong, really you have to rework or reject a huge lot. If you take very small lot sizes, of course you have to take much more samples, but it's up to the producer to decide the size of the lot. Of course, if you have a cleaning session in between, or if you really switch the processing, or if there is a new batch of ingredients used and so on, then of course you cannot call it the same batch. But we consider that it is up to the producer to define, but in a transparent way and clearly, and not coming back to it, a batch size. Any additions, Leon? Or
no, I think you explained it very well. The batch size is kind of open. It's a management decision. What is the risk you lose the batch?
And then the question is, different outbreaks have occurred in the recent months in companies that have established management systems. What commands and recommendations do you have to overcome a situation of this type? Indeed, different outbreaks do occur in the recent months, but also in the last years, and they occur regularly. Unfortunately, but you mentioned they have established management systems. That is always the question, if that is really true. If there is often, if you then look what is going on, you can often find things that are not perfectly managed. But it does, of course, it can occur that everything is under control and still sometimes something goes wrong. But in the many of the big outbreaks that we now see, where there are many people getting ill, if you then look, there are always some indications that it is not really a perfect management system that is adhered to, I think. Leon?
Yeah, and also in well-established management systems, people have to make decisions on the design of a food and a process, on the monitoring they do in terms of different testing for verification, for validation. So there are many elements where things need to be very well controlled. But then, yeah, it's that management decision, and it's the knowledge, the capabilities an operation has that really makes the management system work. Just having an established management system is not saying much in a way. It's really, it's also the underlying mechanisms, the people and everything.
Mm-hmm. Okay, then maybe we do one last question, Leon, before the coffee break. Or
if you have time, we can do it one more, yeah.
And there are two questions that are posted in Portuguese or in Spanish, so maybe other people can translate that, and we can come back to that in later Q&A sessions. But I will take then the question: if a high amount of mold and yeast harm the consumer, why do they have limits on molds and yeast in legislation then? I think the question should be, if a high amount of molds and yeast does not harm the consumer, why do you have limits on mold and yeast in legislation then? Generally, yeasts do not harm the consumer, except, of course, if they produce alcohol and you consume too much alcohol, because that is, of course, also a toxin. But yeast are generally not in any way harming the consumer. But molds also generally do not harm the consumer, except if they make mycotoxins. And of course, there is always a risk if you have a moldy food that mycotoxins have been produced. So mold is not directly harming the consumer, but there is an additional risk that mycotoxins might be present. But those mold and yeast, they were more in the indicator microorganisms, and it is a sign of not good hygienic control. So and therefore these type of things are in the legislation. In legislation, we try to prevent, of course, really pathogens to occur, but also we try to have a little bit focus on quality of the foods. And if things are really spoiled with too much yeast and molds, it is a sign of bad hygiene, and therefore there's a higher risk also potentially of other contaminants that might harm you. Any additions, Leon?
No, it's as you say, it's very much an indication of bad raw materials or hygiene not being up to standards. Very much like other groups, Enterobacteriaceae, coliforms being used for process performance indication. It's good to have them in legislation because that is giving them the reference to what would be a good quality product, what is an expected product of good quality.
So we have had now the first part of our session, and I would like to remind you that it is good to, like it was a lively support by people from YouTube to send us questions. Keep on doing that, but also think about prepare questions for the Thursday panel meetings, because these panels will discuss about the different subjects. So in session 5, we'll look at the challenges and future risk-based food safety management. Where is the world going? We look at microbiological criteria and useful testing, so also related to some of the questions of today. And also specifically managing Listeria monocytogenes, so in peacetime and in crisis. Please post questions on YouTube, but also relate them to these different sessions. And maybe we'll come also back to the questions that have been posed today, like we promised already. So later today, we will now in 20 minutes, we have now 20 minutes coffee break. We will have 3, or even 4, sorry, live virtual presentations by Bob Buchanan, Wayne Anderson, Peter McClure, and John Donnery on interesting subjects. Please come back in 20 minutes, and then Janet Luna and Francisco Garces will be the moderators, and they will introduce these speakers. And remember, again, at the end, there is questions and answer session. So already during the presentation of Bob and Wayne and so on, post already questions on YouTube so that people can already organize them and start preparing the answers. So thank you for your attention for this first part, and see you back in 20 minutes at about 18 minutes, I would say.
Good morning, good afternoon, and good evening. Welcome to the second section of the Latin American Subcommission, LAS, of the International Commission on Microbiological Specification for Food, Icmsf, webinar diving deeper into the Icmsf approach to microbiological food safety management now and in the future. I am Janet Luna from TFC Colombia, and together with Francisco Garces, also from Colombia, we'll chair this session. Today, the webinar comprises 2 sessions. The first session was presented in utility of microbiological sample and testing. In this session, different videos were presented that can be consulted on the Icmsf website. Francisco, please introduce.
Thank you, Janet. I will want to remind everyone that these sessions are being recorded and will be shared to the YouTube channel of Icmsf later. So let's start the second session on this webinar, focus on the developments in risk-based food safety management. We ask you to take active participation and share your questions through the chat on the YouTube video. Our first speakers will be Dr. Robert Buchanan. Dr. Buchanan was an Icmsf member from 1991 to 2011 and a consultant of the Commission since 2012. He is an emeritus professor of food safety in the University of Maryland and has extensive experience in predictive microbiology, quantitative microbial risk assessment, microbial physiology, mycotoxicology, and food safety systems. Dr. Buchanan will talk about the introduction of microorganisms in foods, Book 7, Microbiological Testing in Food Safety Management, Principles, Concepts, and Applications. Dr. Buchanan, go ahead, please.
Okay, and I'm going to call up my presentation, and hopefully that's what's on the screen now. And what I'd like to do is give an introduction to our book 7, which is Microbiological Testing in Food Safety Management, Principles, Concepts, and Applications. And
Bob, sorry, could you make your screen bigger? You are showing just the small screen.
Okay, so let me get back in here and see if I can get this to blow itself up. There it is. Okay, that's about as big as it gets, I think.
Okay.
Okay. So what I'd like to do is introduce to you book 7, and you saw earlier pictures of it in the video clips. In 2018, we came out with a second edition of the book. It looks like, and it's in that same green format. And it's a substantially expanded revision of the Icmsf approach. And my goal here is just simply to introduce you to the book and some of the concepts it covers. Now you'll notice as I go along that there'll be some of the areas that I covered in the video clip, or I'm going to expand on here. I might note the second edition is divided into 4 major sections. These consider the hazards, risk, and risk-based metrics in dealing with risk associated with microbiological testing. It then moves into microbiological criteria, sampling probability concepts, sampling plans, and attribute plans in particular. And then it moves from the original attribute testing into other concepts in microbiological testing, including microbiological methods, the importance of them, alternate sampling approaches, statistical process control verification, environmental testing. And then the book ends with 6 examples of various organisms and commodities to demonstrate some of the principles. Some of these slides you saw in the video clips, if you just watched the video clips. Microbiological testing is a technologically based, statistically based set of tools. And there's different types of testing for different types of needs. And these are the 5 major ones: hold and release batch testing, process control verification, environmental testing, investigational sampling, and surveillance. And part of the purpose of this book is to help you decide which is the tool that you need and how you should use it. So typically when we're talking about microbiological testing, we're going to be talking about attribute testing. And this is going to involve either 2-class presence and absence tests, 2-class numerical criteria where you have an acceptable versus an unacceptable level. We also can move into a 3-class plan where you have an acceptable level, a marginally acceptable level, and then one that is unacceptable. And typically this is going to require some kind of quantitative evaluation here. Now, I might note that when you start applying these, this is these kinds of sampling plans are going to be appropriate for culture-based methods. It's also going to be immunologically based methods and omics-based testing. These all fall back on how you take a sample and what you do with that sample. Now, just to remind you, a sampling plan, what is a sampling plan? And sampling plan includes the sampling method, the assumptions that you make in developing those methods, the sampling locations, the decision criteria, and then most importantly, it should have ahead of time have the actions that are to be taking place when you no longer meet a microbiological criteria. The actual criterion is going to specify the number and size of the samples, the number and size of the analytical units, how often you're going to be testing. It may also tell you where you're going to be testing. If you're going to be doing sampling, or if you're doing environmental, they'll have an indication of where you should be sampling. It's going to give you the assumed defect rate and the assumed standard deviation of the distribution of the organism. And we'll come back to that. It's going to specify the lower limit of detection, the action to be taken if the criterion is exceeded. And then it's also going to need to specify what is the level of confidence that you're trying to achieve out of the sampling plan. So, as I've already indicated, and I just wanted to reinforce it, the utility, effectiveness, and the cost of testing is going to be dependent on all of these different criteria, the inherent cost of the analysis. If you have an analysis that's going to be $1,000 a sample, you're not going to do a whole lot of samples, to be very honest. And now part of this is going to be dependent on the defect rate, the sensitivity that's required in the testing, the distribution or variance, the distribution of it in the lot or whatever unit you're testing, sample unit size, analytical unit size, the method's lower limit of detection, and this is like to refer to, when is 0, 0. And then the confidence you have to have in those results, and all of those are going to have to be specified in it. And the book goes into great detail about some of the things that you need to do this. So we have two types of testings that are most often used in the food industry when it comes to testing foods. We have the traditional within batch or within lot microbiological testing. And this is the test where the goal of this test is to demonstrate the microbiological safety or quality of a single lot of food. And typically this was developed during the time when they were shipping things between countries particularly, and it basically assumes no prior knowledge of the food. So this is where you're taking a lot, you're doing a sufficient amount of testing that you feel confident the food is safe to be used. The second type of testing, and it's actually the type of testing that is more often used, is referred to as between lot testing. And this is often referred to as process control testing. And the purpose here is to verify that a food safety system, which has already been validated, is continuing to function as intended. And it assumes in many cases that you have very much detailed knowledge of the food and the foods that and the processes that were used to get it. And I might note this can extend all the way from the initial primary production on a farm all the way through to the ultimate consumption of the product by the consumer. So typically what we're doing here is the primary role of statistical process control testing is to verify that the food safety control systems are working, that the control is achieved through a series of preventive or intervention control measures, which are being monitored. And this is a way of then checking that those are actively measuring the stringency and the effectiveness. The important thing about verification testing is the fact that it is used for trend analysis. It's used for the identification of other factors or interactions that may be contributing to control, and that the assessment of the controls is functioning as you intended. And so I do want to go through this because this is the type of testing that actually is used most in the food industry. And while we may talk about lot testing and trying to prove that a lot is safe, actually we're in most instances trying to rely on the fact that we know that the process is under control. So we showed some of these in the video clips. And so what we're doing here is we're using this process to measure the loss of control, either due to a process failure or excess variability. And this is just a hypothetical set of data that's collected over time. And the one thing that I can emphasize here is there is a propensity for people that are doing microbiological testing in a QA situation to test. If it passed, that's the last time they think about it. And really what I would emphasize here is the need to be able to look at your performance over time. And if this was a process that typically is under control, what you should be looking for is a central tendency. And then you're looking at the spread either above or below that, where you get beyond a certain limit that you're looking for. Now, in reality, in any kind of a situation, you're going to have occasional samples that are going to go above that. So here I gave just a single point, but you see a central tendency and a fairly strong central tendency and not a great deal of variation from time to time. You can wind up getting a situation where you have excess variability, where you have starting to have you're losing your central tendency, you're having an increased number going above the line in the upper limit, and then you can actually have something going below the line. And when you get into this situation, this often indicates that you're missing a factor that you should be controlling, that you have something that is contributing to this excess variation. And this is an area where you have to go back and say, okay, I need to go back and look at this and find out why I don't have a central tendency and what is not being controlled. We have other examples where you see a trend over time. You have a nice tight central distribution of your results, and then all of a sudden it gradually starts to creep up. This can be caused by a number of different things. What it is basically a gradual process failure in the process of either potentially hygienic situations, or you have some part of the system that you're using to control the organism is starting to break down. For example, you're starting to lose the heating capability in one of one of the sections of your control. Again, all of a sudden you can then have this where you have all of a sudden a very abrupt failure. And this is the kind of situation where you would like to catch it here. You're going to see it starting to ramp up. And what you want to do is be able to take action before you get to this, because this is where you're going to have to start taking product and bringing it back and probably reworking it, etc. And this could be anything from one, you have a failure in your heating system if you're cooking the process, or you have a sanitation process that is breaking down, etc. And then the last one that is often difficult because you do need to look at carefully, and what you need is to look at the periodic process failure. And so here's an example. Again, we have a nice central tendency, a reasonable variation around that central tendency, but every so often, and if you look at them carefully, you have a situation where you have an out of control situation that occurs at a routine time. And so the one that I've seen that where this happens, if you have, for example, a condensation problem, and you're having condensate dripping off the ceiling onto the food, and you all of a sudden have a periodic, a repeating of this process over and over again. So this would be an example of that kind of failure. Now, I might note this, when you're sampling for process variation, the ultimate goal is to take action before the limit is exceeded. This works best for indicator organisms, pathogens in raw materials or raw ingredients, where you can take action before you start using it, or process conditions or food characteristics. It becomes less effective if you're dealing with pathogens in ready-to-eat foods because of the loss of ability for preemptive intervention. Because in the case where you're dealing with ready-to-eat foods, you're still going to have to take action due to current regulations or standards. Because once you get into a ready-to-eat food, you're typically in a different ball game in terms of the ability to release it into commerce. We also have to deal with the reality is that the microorganisms are particulate in nature, and that to be 95% confident of getting at least one cell in an analytical unit, you have to deal with the mean log concentration. And basically what it says is that if you're taking a 1 microliter sample, then your mean concentration has to be up around 20,000 CFUs per mil in the sample you're looking at. If it's 10, it goes up in units of 10. So if you're taking a mil, you're down to dealing with basically 20 organisms. And if you need to deal with this to get around this limitation associated with the size of the analytical unit, you're either going to have to increase the size of the analytical units being examined, increase the number of analytical units that are being examined, or you're going to have to enrich or concentrate. And I might note these are the two. If you're dealing with a liquid food, you're going to probably deal with concentration. If you're dealing with a solid food, you're going to have to deal with probably an enrichment scenario. Now, I did want to introduce concept rates and explain in a little bit more detail and let you look at it in terms of a visual representation. So what I'm going to do is use as an example, picking marbles that have been painted from green to yellow in your process, and you have a big jar of them. You're going to put your hand in and take random samples and look at them in terms of how many marbles didn't get painted yellow. And so if I took 40 samples, and I might note here, if you're yellow or you're green-yellow colorblind, ask me for an alternative color scheme, I can give it to you. This is the color scheme I find that I have the least questions from my audience. So if you do not see green and yellow marbles in this, you should get in touch, and I can give you different color schemes. But if we had a 50% defect rate, 50% of the marbles that I picked out weren't painted yellow, they were green, it would look something like this. And you can see if you have a 50% defect rate, it's pretty easy to determine how many that you have a problem. If I drop it down to 25% of the time, my anticipated response is going to be something like this with my 40 marbles. If I go down to 10%, now I have a much smaller portion. And now I get down to 1%. And the most likely scenario here, if I pick 40 marbles, is I wouldn't see any green marbles. That does not mean that there aren't green marbles still in this, because now what you're happening here is your sampling is now limited by your defect rate. So just to put this into a perspective, if I have a 1% defect rate, and I know that seems low, one needs to consider the volume of food produced and consumed. So let's assume that we're producing 10 million packages of cookies, and they're being produced and consumed every day. So if you have 1% of those cookie packs are contaminated, you're not going to be likely to actually with a reasonable number of samples, detect them microbiologically. But that 1% would represent that you've released basically out into the marketplace 100,000 contaminated servings. And then if we were dealing with actually people eating them and getting sick, say if we even assumed that we had 1% of the people that ate the contaminated servings became sick, you would wind up with 1,000 cases of salmonellosis as a result of that. And these are going to become more and more important when we talk about alternate ways of detecting foodborne outbreaks. Now, the calculations that are used to determine the number of samples that you need to detect should be done ideally with a process called power calculations. And there are standard programs for doing this. I like to use some shortcut formulas, and what I will tell you here, what I'm giving you here is it gets you an approximation, and it's good enough for the back of the envelope calculations. And this one, ST, which is the number of servings that need to be tested, is equal to 2 divided by the defect rate. And if you want, that's for 95% confidence. The second one is if you want 99% confidence that you are able to detect a contaminated lot, then you would use the sampling number would be 3 divided by the defect rate. And this has to do with standard deviations. But just to give you an idea, and it gives you the magnitude of difference, if I'm working with 30% of the servings are defective, okay, to be 95% confident that I would detect that level of contaminations, you would need to take and sample 7 servings. If I wanted to be 99% confident that I detected a contaminated lot, I would have to take 10 servings. Pretty easy, certainly within the estimates that we're usually work with in terms of testing microorganisms. However, if I had a 0.5% servings were defective, in order to do that, I do the same calculation, and you can see to be 95% confident that I'd have to test 400 servings. And if I want it to be 99, the reality is that when you get up to this low defect rate, you're not going to be able to do this. The cost of testing will be outrageously expensive, and so you're probably going to have to do alternative approaches. The other thing that we deal with is the homogeneity of the distribution, and particularly when we're doing low levels of contamination, there are different systems. Traditionally, we take random samples when we're dealing with microorganisms. And this is good if you have a fairly large number of samples, say 30 plus. The alternative is to take systematics, where you look at the entire lot and you're taking samples over the entire lot and taking X number. This one is good or better when you have low levels of contamination. However, it can give you a problem, for example, if you have a periodic effect of missing it. And then the last one is stratified random testing. And this combines stratifying all the samples and then taking them at different times. And this is an important concept. And certainly if you're at low levels of contamination over a very large lot, it's highly recommended that you move to something like this. Okay, and then just to let you know here is just to show you some of this is this is some examples that what we did is simulation modeling. And simulation modeling is a very powerful tool, and some of your best friends you need to be is with people that know how to do this kind of simulation modeling, because this looks at 3 field samples that we did in the study. And so I believe I didn't see my red light yet, but I would say that this is the kind of thing, and this looks at 3 different sampling plans used on fields of lettuce, for example. And one of the standard patterns that's used is a Z pattern. And so, and this looks at random versus stratified random, and this is looking at basically taking 30 samples. And you can see the random and stratified random gives you a nice tight fit. The Z pattern, because you don't sample some of the field, gives you either too much or too little, and winds up you could get really faulty results on that. And then finally, I wanted to say, what does zero mean? And so the standard question is, if I had 1 million servings of a food, how many of those servings would I need to test to be absolutely sure that I adhere to a zero tolerance standing? And I always remind people that the answer here is you'd have to test all 1 million servings. And then, of course, there would be nothing left for people to consume. So you're always going to have some, what you're looking for here is to be testing enough that you're going to meet the requirements for your putting food out into commerce. And you're not going to be able to test them all. And I know I'll be talking a little bit more about that, about the changes that have been taking place in session 6 and 7. So I think with that, I would like to end it here. And I think I'm on time. And so I'm going to stop my share and turn it over to the MC.
Okay, thank you very much, Dr. Buchanan, for your presentation about Book 7. The question are at the finish of the session. The next speaker is Dr. Wayne Anderson. He is Icmsf member since 2007, Director of Food Science and Standards of the Food Safety Authority of Ireland, adjunct professor with the University College Dublin. Dr. Anderson, we talk about establish performance objectives through the chicken production chain to achieve control of Campylobacter. Dr. Wayne, welcome.
Can you hear me now?
Yes.
Excellent. All right, start my video. Hopefully you can see me as well. Oh, we're getting good now. Excellent. Right. So what I was hoping to do, can you see the screen that I'm sharing now as well?
Yes, we can see it.
Yes.
You can go into presentation mode if you want, but we can see it the way that it is.
I'll put it onto presentation mode and we'll see where. Oh, have you got it there? Yeah. Everything okay?
Yeah.
Excellent. Right. Well, sorry for that. I was having a bit of a problem with my screen earlier. So thanks very much for the introduction. I work for the Food Safety Authority of Ireland, but today I'm going to be speaking on behalf of the Icmsf rather than the Food Safety Authority, just to be clear. And I'm going to talk about establishing performance objectives and using the chicken production chain and Campylobacter to illustrate how you might do that. And it's going to be quite complicated to do this in a short time, but I'm going to do my best. I think the first thing to look at is how do we design food safety controls? For many years, food safety controls were hazard-based and control activities were focused on reducing hazards. In some countries, that's still the case, but over recent years, risk-based approaches have gained acceptance, certainly in the EU and a lot of other countries around the world, and official controls are supposed to be based on risk. So there is a clear correlation between reducing hazards and reducing risk, but that relationship isn't always linear and direct. Often we forget that there is a cost to reducing hazards both financially and in time and effort, and there can also be an effect on reducing consumer choice when products have no easy control step. An appraisal of the risk allows us to determine the appropriate level of hazard control to achieve an acceptable level of public health protection that balances these factors. So risk allows us to aim for a non-zero hazard target that achieves a public health goal. So non-zero is the key bit there. But the other a thing that's important is flexibility in the way those controls are achieved. So if my goal is to get from home to my office, which is the map you can see here, Google Maps is great because it gives me a few alternatives and it even lets me see the consequences in terms of time should I choose to go each alternative route. So don't get me wrong, I'm not saying that we should allow the food industry ad hoc to decide on what level of public health protection they wish to achieve, because that's really a societal decision. But I do think that our standards should not be so prescriptive that the industry can't design different ways to get there. And this is the basic concept behind risk management metrics, which we will be discussing in the remaining slides. In 2007, Codex document Principles of Risk Management, they placed risk management metrics into the International Food Standard for the first time. And these are well-known ones, and these are the probably less well-known and used ones. In my presentation, we will discuss a hypothetical process for setting food safety objectives and performance objectives for Campylobacter in poultry, with the emphasis on the hypothetical. It won't be real. And I will also show the microbiological criteria that could be used to verify achievement of that performance objectives. And Bob just talked about the purpose of some of this sort of sampling and testing. Remember that an FSO, a food safety objective, is set at the point of consumption based on public health goals so that it can't be easily measured because it's the point at which someone puts the food into their mouth. Therefore, a performance objective has to be set at earlier points in the food chain, and these can be measured, but they have to be able to be linked to the achievement of the food safety objective if a public health goal is going to be achieved. So that's how it all links together. The Icmsf introduced an equation to summarize how industry could design food safety systems to meet a food safety objective. It recognized that the sum of bacterial log reductions in production system, which is the sigma R bit here on the equation, when subtracted from the product of the sum of bacterial log increases during a production system, which is the sigma I bit, and the initial log number, which is the HO bit, it needs to be less than or equal to the food safety objective if the public health goal is going to be achieved. If the equation is applied to a whole production chain in a stepwise fashion, then that starting number, the HO, at the start of a process step is actually equal to the performance objective of the step before it. And that'll become obvious, I think, hopefully, as you go through. So in effect, what we can do is we can set POs, the performance objectives, for each step of the production chain, which works together in sequence to achieve the food safety objective, which of course then allows you to meet the appropriate level of protection that we want to achieve. So setting a food safety objective is quite a challenge, and there are a few examples, and I should say actually very few examples in national standards globally. Food safety objectives are as defined by Codex is the maximum frequency and or concentration of a pathogen in a food at the time of consumption that provides or contributes to the appropriate level of protection. The appropriate level of detection was defined in the SPS agreement, as you can see here, but finding concrete examples around the world is quite elusive. It seems that governments are not really prepared to articulate quantitative appropriate levels of protection, maybe for political reasons, maybe because they don't feel they have the scientific basis to do so. But that does make things difficult when you're trying to actually then do a back calculation based on those appropriate levels of protection. Now, fortunately, there are papers like this one from Dutch colleagues that seek to quantify what could be described as an inferred appropriate level of protection. And it does this in terms of the current burden of disease. So basically what they say is that if we can measure the current burden of disease, we should be able to derive what the appropriate level of protection is under those current conditions. And here are some of the examples of current conditions. It's like food safety controls, population variability, food consumption patterns. So there's an assumption obviously here that what you currently have is what the government accepts as a level of protection. Probably isn't true in all cases. I think we'd all like to get better. So with those basics behind us, I think we have to take us through an illustrative example of how to calculate an appropriate level of protection for Campylobacteriosis from chicken consumption, which can be then used to derive a food safety objective, which in turn can be used to calculate the performance objective for chicken at the end of retail. All this and the earlier POs for the chicken production chain can be found in full detail in chapter 19 of the Icmsf book 7, second edition, which is available from Elsevier. So chapter 19 goes through all of this in a lot more detail. So here is an example of a derived ALOP for illustration. Using the paper from Elaine Scallon and colleagues, we have good figures for the burden of foodborne disease in the United States. And for Campylobacter, the rate is 2,826 cases per million population. The European Food Safety Authority's risk assessment on Campylobacter in poultry estimated that up to 30% of cases of Campylobacteriosis were attributable to handling, preparation, and consumption of poultry. To derive an ALOP, we apply the upper attribution rate of 30% to the estimated number of foodborne Campylobacteriosis cases in the US. And that gives us an appropriate level of protection of 848 cases per million population attributable to poultry consumption. Now, obviously here I'm assuming the EU attribution data applies to the US, which of course is unlikely, but would have to be verified. But it is just an illustration I'm trying to do here to show you how to do these calculations. Often we're not content with the amount of foodborne disease that currently exists, as I said earlier. So governments set public health goals at a much lower level. And these can be applied to the existing ALOP to derive a new appropriate level of protection should the public health goal be met. So for example, the appropriate level of protection we just derived could be subject to a public health goal to reduce the cases of Campylobacteriosis due to poultry consumption by 50%. And that, if I can hit the right clicker, would give us the new ALOP of 424 cases per million population. So what we're going to do is we're going to look now at how we might design food safety controls to meet this new public health goal ALOP of 424 cases per million population. Okay, so having set our ALOP based on our public health goal, we now have to look at deriving a food safety objective, which in our example will be the number of Campylobacter per gram of poultry meat at the point of consumption. So that's what we're going to do next. And in 2005, Marcel described a scheme for calculating an FSO from an ALOP per million population in this paper I'm just showing you now. He published this equation, which I'm showing here, where ALOP was the product of the amount of Campylobacter consumed and the probability of illness having eaten one bacterial cell, which is derived from a dose response model. So that's how the inputs you need into this equation. The dose of Campylobacter consumed at an eating occasion is, of course, the amount of chicken consumed, the mass of chicken consumed, multiplied by the concentration of Campylobacter on that chicken per unit mass. Concentration of Campylobacter on the chicken per unit mass is then the FSO, but expressed in an arithmetic unit rather than log units. So that's why there's the way it's shown at the moment. So if we replace the dose D in our ALOP equation from the last slide and rearrange the equation, we can get an equation that allows us to derive a food safety objective from the ALOP, which you can see here. To use the FSO equation, then we have to have the other values, and one of them is the probability of illness, which is little r, following consumption of one Campylobacter cell. And so I'm calling this step 2a. So to work out this, we need a dose response model. And as I said, it takes a two-step approach. So first off, we calculate the probability of infection given consumption of one cell from the dose response curve. And this one for Campylobacter was published by the WHO. And we find that there is a 1 in 288 chance of infection after consumption of a single Campylobacter cell. So that's the chance of infection following consumption of a single cell. In step 2b, we have to find the probability of illness given infection. And for this, we can use the human feeding trials published by Black and again reproduced in the WHO risk assessment for Campylobacter in chicken, where the numbers infected and the corresponding numbers getting ill are given, as you can see here. Here we find that there is a 1 in 3 chance of getting ill if you're infected by Campylobacter. So R, which that value we're trying to find, which is the chance of getting ill from consuming 1 cell of Campylobacter, is actually the product of the 2 probabilities. The probability of infection after consumption of 1 cell, and then the corresponding probability of illness having been infected. And this leads to a 1 in 885 chance of illness having consumed a single Campylobacter cell. So that's what the dose response model tells us, and that's our value of R. So the R value can now be inserted into Marcel's equation, along with the values for the mass of chicken meat eaten in a meal and the number of eating occasions. And both of these values I got out of the WHO Campylobacter risk assessment. And then you also add in the appropriate level of protection that we calculated at the start. And we're trying to achieve that given FSO. And we find that the food safety objective is equivalent to about 1 Campylobacter cell per 28 kilograms of cooked chicken. Because don't forget, we're assuming that normal consumption is cooked chicken and that FSO is at the point of consumption. So this is the amount of Campylobacter that you would want to have in, maybe not want to have, but you could tolerate to have in cooked chicken if you were going to meet that ALOP we tried to do earlier, which is your public health goal of reducing the level by 50%. Okay, so now we have an ALOP and we've derived the food safety objective, and we can move on to calculating a performance objective for the end of the retail step, which is the first step leading into the consumer. And so here, the PO is a concentration of Campylobacter per gram of raw chicken in the retail store just before it's purchased by the consumer. So that's the PO we're looking to calculate. And if we go back to our Icmsf equation I showed at the start, we can modify it to meet that purpose. Here, the reduction step is given by our home cooking by the consumer. The starting cell number, which we've called here, is H0C, which is the consumer stage, just to differentiate it from H0s in other steps, is the same as the PO for the raw chicken at the end of the retail. So that's the one we want to calculate. The increase is given by 2 things: the growth during storage, and the number of Campylobacter that might be transferred onto the cooked chicken due to cross-contamination, because we know cross-contamination occurs when people are preparing chicken in the home. So that's the inputs for this equation. Now, if there's no cross-contamination, everything's quite straightforward. For illustration, I took the USA recommended cooking time temperature, which is stated by the Icmsf, to achieve at least a 7 log reduction of Campylobacter. So in that case, the sum R is 7. And as Campylobacter won't grow at chill, and I'm assuming that the chill chain here is respected during home storage, not always the case, but let's assume it is in this case, then the sum of G, the growth, is 0. There's no growth. This makes the calculation of the PO quite simple, since it's simply the FSO plus the sum of the reductions, which results in a value of less than or equal to 2.55 log CFU per gram of raw chicken. So if everyone stored their chicken at chill properly, cooked their chicken well, and observed good hygienic practice in the home, then we could tolerate 355 Campylobacter per gram of raw chicken at the end of the retail and still achieve that improved ALOP and the FSO that we derive from it. So that's the ideal situation, but of course we don't live in an ideal world. And cross-contamination is a real problem in the home because people just don't follow good hygienic rules all the time. Now, Petra Luber from Germany and her colleagues measured the cross-contamination transfer rate of bacteria and Campylobacter onto cucumber prepared using a knife and a board previously used to prepare raw chicken. So that was some data that I came across. And for illustration, I've used this transfer rate for cooked chicken. So cut on a board and with a knife and used to prepare the raw chicken without proper cleaning. So I've used the same transfer rates. Around 0.1% of the bacteria on the raw chicken transfer to the cooked chicken. So the bigger the number of bacteria on the cooked chicken, the more get moved to the bigger the number of bacteria on the raw chicken, the more get moved onto the cooked chicken. And that's an arithmetic process, not a log process. Unfortunately, Marcel again provided an equation to calculate that contamination in log CFUs per gram. And here it is. And of course, the probability of poor hygiene in the kitchen is not 1. But if it happens 10% of the time, then we get the FSOs in column 3. And if it happens 1% of the time, then we get the FSOs in column 4. So the conditions of log starting number of Campylobacter and the probability of cross-contamination that allow us to meet that food safety objective we chose earlier, they're all shown in grey. So for example, if there are 100 CFU per gram or more of Campylobacter on that raw chicken at retail, which is an HO of 2, then the probability of cross-contamination happening must be around 0.01% or less to meet the food safety objective we want. If it's higher than that, we won't meet the food safety objective. Redmond in 2004 observed under observational conditions that greater than 50% of people who prepared chicken failed to properly decontaminate boards and knives. One way to achieve a very low probability of cross-contamination is to provide, I suppose, oven-ready chicken that can be cooked in a bag. And this is in fact becoming more and more popular in Ireland, for example. So now we have an ALOP of we can then use it, we have used it to calculate an FSO, which we have used to then calculate a PO for the chicken at the end of retail, given a low chance of cross-contamination of less than 1 in 1,000 preparation occasions. I reiterate that this can easily be achieved. Sorry, I'll just go back one. It can easily be achieved if the chicken is ready to cook in the bag, for example, or consumers are sufficiently informed to cook as instructed. For our illustration, under these circumstances, a PO at the end of retail could therefore be 1.495 log CFU per gram raw chicken meat. Now, clearly, if cross-contamination happens more frequently, as it probably does, then we can tolerate less Campylobacter on our raw chicken at the end of retail than this illustration, in which case that PO is going to be a higher number. So it's important, however, to verify that that PO is being met. But we rarely macerate an entire chicken to find out the contamination level. So instead, it's quite common to put the chicken in a bag in a plastic bag with 100 mils of rinsate and agitate it to remove all of the surface Campylobacter to give a concentration on the surface of the bird. So to operationalize the PO, we need to convert it into a concentration per mil of rinsate rather than a concentration per gram of chicken. And here I've used some values given by Australian colleagues to do just that. And the PO becomes about 2.49 log CFU per mil of rinsate. And there are certain assumptions in doing this, of course, but again, it's for illustration purposes. In setting a suitable microbiological criteria, a risk management decision then has to be made on what proportion of batches are going to be allowed to be above the performance objective. In other words, what is our acceptable level of confidence that the PO is going to be achieved in all batches tested? And you can see from the distribution that I've set that this is at 99%, so only 1% are allowed to be above the PO in my example. And using the Icmsf sampling plan calculator that we have available on the web, and an assumption about the standard deviation, which in this case is 0.6, the contamination of a batch, you can see that the 3-class plan as proposed will provide a desired verification of the PO. So if as a competent authority I set that criterion at the end of retail for verification of a well-controlled process, I would have some confidence that the industry was doing its job throughout the chain and that we would achieve the FSO with the consumer, providing I'd done a lot of work to get the consumer to actually handle the product properly. Unfortunately, I don't have the time to go through the whole pathway showing calculations of POs, so this is the final outcome of chapter 19. We've only looked at the bit in blue today, which is that bit at the bottom, but you can see that the different interventions along the chain allow different POs to be set, some more stringent than others, depending on what process is being used. So for example, Campylobacter dies off at frozen temperatures. So if frozen chicken is sold at retail, a much higher PO at the end of slaughter can be tolerated than if the chicken is sold at chill. Similarly, if you do wash the birds, eviscerated birds in some chemical like ASC, followed by immersion chilling with chlorine, a much less stringent PO can be tolerated to achieve the same FSO. What all this shows is that if you're a government and you're setting that FSO, then the government and the industry can work together to set the different POs that achieve that food safety objective at different steps in the chain. The approach sets a clear target that must be achieved, which is the food safety objective, and then the industry can find any number of suitable ways in which to achieve it within the confines of regional law and what they're allowed to use on their poultry. So if a country doesn't want to allow chemical treatments during slaughter, then the chickens have to be less contaminated from the farm, and then biosecurity becomes the main focus. And if a country doesn't want to make farmers invest in high levels of biosecurity, then the birds, of course, have to be cleaned up at slaughter in some way, and then you have to allow interventions to kill the Campylobacter on the chicken. So I hope I've illustrated the importance of preventing cross-contamination in the home and why the level of Campylobacter on retail chicken must be low in order not to overwhelm the consumer's hygienic practices. And that becomes a very, very important for how much Campylobacter we can tolerate on the chicken that's sold at retail, and then the consequent levels of Campylobacter that are tolerable on different points in the chain. And that really concludes what I wanted to go through today. A bit of a whistle stop, but as I say, chapter 19 goes through this in far more detail, and that's where you can have a look if you're really interested in going into this in more depth. Thank you very much.
Thank you very much for your presentation, Dr. Anderson, and for the quite illustrative example. Our next speaker is Dr. Peter McClure. Dr. McClure is an Icmsf member since 2011. In 2014, joined Mondelez International as the section manager for food safety for the European, and moved into the role of principal scientist, a microbial member of the advisory committee on the microbial safety of food in the United Kingdom. Dr. McClure, the floor is yours.
Many thanks. Thank you very much for the opportunity to talk today about Book 9, and I'm just going to share my screen now. Can you see the screen okay?
Yes, thank you.
Great, okay. So, so far today, we've been talking mostly about the existing books and material in the existing books, the concepts, the equations, the approaches that Icmsf have developed over a number of years to establish a very good sound basis for testing, sampling, looking at statistics of process control, and that type of thing. And the subject that I'm going to cover now is a bit of a departure from those concepts in that this work is still in development. So this is a work in progress. So if you go to look for Icmsf Book 9, you won't find it because it's not published yet. So this concept that the main thrust of this book is to look at the context of global megatrends and how they might impact on food safety and food spoilage or food quality, and then how Icmsf tools and thinking can be used to be applied in the context of those megatrends to retain the resilience of the food chain in terms of food safety and food quality. So the main objectives of the book are to, firstly, to provide an assessment of megatrends that are relevant to food safety and food stability, or food quality, if you like. So by the word stability, I'm referring to spoilage or food quality. And this main objective, the first one, is to assess the main drivers and trends likely to affect the future global food value chain. The second main objective is to look at the various impact assessments that could be applied to those situations, considering these megatrends, how they're interacting, and then to explore the use of systems thinking as applied to global food safety system in order to help develop our position in terms of global food safety and security management for maintaining and indeed improving food safety and food quality. So this is what we mean by resiliency. The third part is to consider developments in the science of food safety and stability, and to look at future research needs and challenges in terms of the development of a risk-based approach for global food safety. So maybe one of the things that will come to mind when you hear this is what do we mean by megatrends and what do we mean by drivers? Because we use both of those terms quite a lot within the current thinking and discussions about the chapters in the book. So by megatrends, we're talking about large, could be social, like economic, political, environmental, or technological changes that are slow to develop and slow to form, maybe with a timeline of 10 to 15 years, but have a global or large scale impact. And the focus here for us is still on food safety and food quality. So that remains the focus of book 9, the concept of book 9 that we have in progress at the moment. By drivers, we're referring to, these are mostly developments that are causing the change. So a driver is the underlying cause of one or more effects that you might see. And a good example of that might be increasing sugar intake in our daily food consumption is a driver for obesity. So those are the main objectives that we have for the book. In terms of the structure of the book, but please bear in mind that this is very much a work in progress, and some of these may change. They may change order, they may change title, they may change in terms of the content. But the main these main chapters and sections that you see here are the current main sections of the book. And it's split into 4 main sections after the introduction, which goes into the history of Icmsf and so on, and introduces these concepts of megatrends and themes. The first section is to look at those megatrends and identify those that are relevant for food safety and for food quality. We've split those up at the moment into buckets, if you like, of first one being sustainability, then food security. Then we have a section on people, which is about population growth, socioeconomics, and food safety knowledge of people involved in the food chain. That includes manufacturers, it includes governments, it includes consumers as well. So all the players in the food safety value chain. Then within that megatrends and themes section as well, we also have a section or chapter on technology and big data. And John will be talking in more detail about that following this presentation. So I'm not going to cover that in any detail and leave that for John to cover. Then there's a section on food technology, which is all about new developing food technologies that are being used in food manufacturing that might have an impact on food safety or food quality. The last part of that megatrends section is about emerging hazards and risks. I'll go into a little bit more detail about the types of things we're expecting to cover in that chapter. The next main section of the book is going to be responding to those megatrends, looking at impact assessments, looking at interventions that we might make at different stages of the value chain. And we also have a section on fit for purpose criteria. And it's interesting that we had a couple of questions earlier on today about criteria, some questions about yeast and molds and other criteria that are set. And one of the main aims of this chapter is to talk a little bit more detail about how to set those criteria. Then we have a section on case studies. These are the case studies that we've identified at the moment. So we're trying to pick different commodity types that use different technologies, maybe have different intervention steps that allow manufacturers and growers to control pathogens and spoilage organisms on their products and on fresh produce, for example. The examples that we've got at the moment are, we've got a fresh produce example, which is focusing, I think, more recently on the leafy greens rather than the tomatoes. Then we have a section on an example on maize, an example on chicken, an example on a dairy product, and an example for shrimp. Then we'll close the book by looking at some conclusions, drawing conclusions from the impact of these megatrends on food safety and quality, and then trying to look at maybe some future needs, future research that's needed, and trying to anticipate what the challenges and opportunities will be with these megatrends that are appearing. So to say a little bit more about the earlier chapters, sustainability, what do we mean by sustainability in the context of food? So we're talking here about products which have a low environmental impact with low consumption of soil and water as examples, products with low carbon and nitrogen emissions, being respectful of ecosystems and biodiversity, and being attentive to local needs and the enhancement of the areas in which these crops are grown and where the food is eaten. Sustainable foods have to be healthy from a nutritional perspective, and very importantly, have to be accessible to all. Those are the principles of what we mean by food sustainability. In terms of the structure that we have at the moment for this chapter, we will start the chapter by talking about a description of the megatrends that are relevant to food sustainability. We'll talk about the drivers, so the underlying causes that are driving change that are impacting or could impact on food safety and spoilage. Climate change is an important trend that is happening. People sometimes refer to it as a megatrend. It has a major consequence on the way that we see food in terms of safety and quality. So it has to be included as one of the major factors that we consider when talking about food safety and food spoilage. We need to cover water resources, so the use of potable water and the use of water in manufacturing, growing crops and so on, and in manufacturing as well, cleaning and so on, all has an important consequence for how we manage safety within the food supply chain. We'll be covering things like biodiversity loss, energy, food versus fuel. So this argument about using land for growing food versus fuel, and also talking about the Sustainable Development Goals as well. This chapter will close by talking about the impact of drivers and responses to these, and then some consequences for food safety and food spoilage. The food security chapter is the next chapter in this series, looking at megatrends, and we will be looking at early on about when we talk about food security, we're talking about having reliable access to a sufficient quantity of affordable and nutritious food, and a continuous supply of that food as well. So we'll be considering the impacts on risk and how to respond and address these changes in risk that are coming from these the megatrends that impact on food security, and then looking at some of the points that Wayne's just been talking about, the food security, the food management, the metrics that are used, and using a systems approach to look at food safety and in the context of food security. Then we'll be looking at responses, developments to increase food security, looking at waste minimization, considering things like shelf life, use by dates, consume by dates, that type of thing, that are all getting caught up in this aspect, the important aspect of minimizing waste in the food value chain. Then we'll be looking at some of the consequences for food safety and stability of the responses that can be made. So it may be that when you look at, for example, the scale of production and manufacturing that goes on nowadays compared to some years ago, the consequences of mistakes or contamination occurring can be absolutely huge. So if a large dairy producer producing dried milk, for example, has a problem with manufacturing, as John quite rightly pointed out earlier on, these things are still happening today on a large scale. And when manufacturing companies have a problem with large size lots, it can have a huge impact on both the number of products affected, but the consequences for consumers. And we have to think about the consumers as the most important player in this, because we are talking about food safety and food quality. So we'll be talking about or considering some of the risks associated with development of new production areas closer to places where food is needed, for example, new hazards that might be emerging from a change in those manufacturing environments, considering things like increased costs, water quality, recycling, and those types of things. You'll notice that there is some crossover here between this chapter and the previous chapter when we're talking about water quality, for example. So we will be careful to make sure that these individual chapters focus mostly on the aspect that they is the focal point, so food security in this case. And in all of the chapters, the early chapters, we'll be looking at these new approaches that could be taken in terms of food safety and stability. So we'll close this chapter by looking at systems approaches that could be used and are currently used at the moment and being developed. The third main component of the megatrends chapter is about people. In here, we're talking about climate change as well, or considering climate change. We're also focused more on population changes, socioeconomic changes, urbanization, and changes in dynamics of populations as well. So we'll be thinking about, for example, the more elderly populations that are developing in some countries as a consequence of better healthcare and so on. We'll also be talking about or considering political influences, human displacement, cross-border conflicts, war and conflicts, and those things that can have an impact on displacement of people. Even things like terrorism to cover deliberate tampering and policies on nutrition as well. Another important point about people is about technology, information, and communication. And you know, when we think about some of the things that continue to happen in food safety, in terms of food safety and food quality, there are so many cases where the same thing happens again and again. And this means that the communication is not optimal. So we're not learning our lessons well enough to prevent these things from happening again. And there are big ways in which communication can be improved to ensure that lessons are learned, or that the lessons learned are more readily communicated and taken up by manufacturers, by consumers, and by all the players in that food value chain. The last part of this section will be about disasters and environmental consequences, so economic effects on food safety issues, impact of food supply chain, accessibility, practical things from a manufacturing perspective like inspections and official control audits. You know, that we have some standards, some very good things that are in place at the moment, but as we talked earlier, even though those systems and standards are in place, things still go wrong. So there are things that can be improved there as well. Another consideration will be lack of laboratories, less sampling, and this is a very important aspect of food safety as well. Remote auditing and confidentiality and self-declaration. Now, as many companies have experienced over the past 2 years, because of the restrictions in travel for COVID, then it's meant that many of the checks that a company would normally do by physical visits have had to be done by remote audits. And those things have consequences. When you do a remote audit, you don't see the things that you see when you walk around a manufacturing facility. So there are some disadvantages and advantages probably from doing remote auditing, but the consequences of those things need to be considered, and the importance of the things that you miss need to be considered. So I'm not going to cover technology and big data because John is going to be talking about this in a bit more detail. Let's come on to food technology, which is one of the later chapters in the megatrends section of the book. So the main focus of this chapter is on new intervention and manufacturing technologies that have a potential impact on food safety or food quality. So we're going to include things like non-thermal processes, like, for example, high pressure processing, and thinking about those technologies that are in development, but also thinking about some of the technologies which are referred to commonly as blue sky in terms of their development. So they're quite a distance at the moment from being implemented, but there is a big interest in those technologies. We'll be thinking about things like 3D printing, fermented foods, novel protein sources like insects or algae, and lab-grown meat, that type of thing. Advances in process control and monitoring, intelligent packaging. These are the things that we're thinking about including that could have an impact on a negative or a positive impact on food safety or on food quality. The main purpose of the chapter is to talk about the technologies that are likely to be the main game changers and give an indication of the direction of travel that those technologies will have, either negative or positive, on food safety and security, food safety and quality. So the purpose and scope is to consider the likely changes in technology, to provide some guidance in anticipating the impact on food safety before implementation, and to produce data that enables a risk-based approach to be applied, and also to help inform regulators, those responsible for food safety, on data and principles to follow to allow regulators to understand the impact of new technology developments. A very important part of that will be the principles that appeared in Catherine Swanson's presentation that you saw earlier about the importance of validation. Okay, so this first step in, particularly when you're talking about new technologies, the first step of validating and making sure that you're controlling the hazards and the target organisms that you want to control, and you're controlling them to the right level, is very important. The last part of the megatrends section will be on emerging hazards and risks. So here we'll be talking about including some definitions of and some examples of major foodborne pathogens identified since the 1970s. We'll be choosing to look at the factors that have led to their emergence. So things like evolution of the organisms themselves, whether that be genetic or epigenetic. We'll be talking about things like host dynamics, which can have an impact on emergence of new pathogens. Things like host jumping or spillover transmission. Things like changes in host demography or vulnerability. Changes in host behavior. So for example, let's say a new region decides that a new product is really attractive to consumers. It's a completely new way of consuming the product, and let's say you're eating a product raw. And these things can have an impact on food safety, and changes in host behavior can have an impact on development and emergence of pathogens as well. Some years ago, when the increase in cases of Campylobacteriosis were being looked at in Europe, it was an interesting finding that focused on the elderly as a population that was being more exposed to Campylobacter than the younger populations, and the dramatic increase in Campylobacteriosis cases seen in that age group was really significant compared to the other age groups. So these things, like changes in our behaviors, will have an impact, and we need to anticipate what those impacts will be. We'll be thinking about primary drivers and factors in terms of pathogen emergence, so host and reservoir factors, intensification, urbanization, movement of people, and so on. And then we'll look at some particular examples that are real examples, and we've chosen the list of examples at the moment includes Vibrios because of the change in the effect of climate change on temperate waters that will support growth of Vibrios in estuarine and sea environments. We'll be talking a little bit about antimicrobial resistant Campylobacter, the situation in New Zealand that has occurred recently, Nipah virus and Citrioviridin in rice. So those are the examples that we've got in our cases at the moment in our list that will be covered in that section. And then we will also have some examples of spoilage. But some examples here include psychotrophic Clostridia in vacuum-packed meats, Bacillus in UHT milk, black aspergillus in grapes, and preservative-resistant yeasts. These are all things that have developed in terms of food spoilage issues, food quality issues over the past 10, 15 years or so. This is an example of how we will look at the various factors that impact on, in this case, antimicrobial resistance, Campylobacter. So you can see on the right-hand side, we have host dynamics, humans to wildlife spillover as a consideration, wildlife to poultry spillover as another consideration. So in this case here, we're talking about the main hosts being poultry, but humans contributing to that host range as well. Talking about movement of wildlife as well. The things that impact on evolution are things like antimicrobial use in humans, antimicrobial use in animals as well. Those all will both contribute to development of antimicrobial resistance capability in Campylobacters that are exposed to those types of stresses. And an example of the impact of amplification would be the intensive production of poultry in some countries that is occurring at the moment. All of these things leading to emergence. And by emergence here, we're talking about an increase in the number of cases of illness linked to a particular pathogen. That could be for any of these reasons of movement, host dynamics, evolution, or even amplification. The next main section of the book will be looking at impact assessment. So in this section, we're hoping to develop a set of tools looking at how you might consider the impact of megatrends and looking at some specific examples that have already been developed, for example, with Vibrios in relationship to climate change. Some of those can be taken further forward and then connected to the processing and the handling of those materials that are then used to produce foods. So much in the same way that Wayne has described for Campylobacter in poultry, looking at those different steps in the value chain, this chapter will look at the types of tools that could be used to connect the drivers, the megatrends, to impacts on food safety and food spoilage. And we're talking later on about characterizing impacts on risk, developing impact models, so including things like model selection, development of models, using things like expert elicitation and multi-criteria decision analysis, which is a common tool that's used when you've got multiple factors coming together that have a consequence for an output. And in this case, the output is food safety or food quality. And then looking at scenario analysis, intervention systems that might be put in place to mitigate the risk that is imposed by changes in, let's say, climate change or these other things that are going on. This is probably the most challenging chapter in terms of how we develop the themes and how we put together the tools as a package that would allow people to look at developing risks. The next main part of this middle part of the book is focusing on fit for purpose criteria, and we had a question earlier on about fit for purpose criteria. Why are standards, why are limits set for particular organisms? And we will come back on this point in the book to talk about the concepts, the main building blocks that should be used to develop criteria. We'll be talking about giving some definitions, examples, particularly of ALOPs, and then how you develop a specification for those, and talking about sampling plans as well. Some part of this will be talking about the impact of inappropriate microcriteria in the food chain. So we will try to provide some examples of where criteria have been set that maybe not a good idea, maybe not a sensible thing to set as a criterion. And we'll give some examples of criteria set for raw materials, finished products, why they're inappropriate or appropriate, and then some of the consequences of getting that right and getting that wrong. The case study example chapters are pretty much the last main part of the book. In these case studies, what we'll be doing is looking at going through the supply chain for those particular commodities, looking at the hazards that are relevant and important and might be relevant and important for the future as well. And then looking at hazard analysis, description of those hazards, where each of these occurs, and existing control measures. And one particular example that is always a good example of where things can change in terms of food safety is his example with 0157 and fermented meats. And back in the early 1980s, when the first outbreaks occurred with beef burgers or hamburgers in the US, there was clearly a very early recognition that burgers and similar products were susceptible to 0157, and that things needed to change in terms of control. Then that extended to fermented meats and to fruit juice. And in the case of fermented meats, there was a publication quite early on, before any of the outbreaks, that looked at the survival of 0157 in a fermented meat. Publication by Mike Doyle, really good publication, but none of the fermented meat manufacturers took a serious note of that, because what they should have done, from seeing what was happening with beef burgers and meat, was looking at the impact of that on their own products. If they'd done that, they would have realized that they needed to look at a new hazard for their products, these fermented meats using beef as a raw material. And if they'd done the validation studies that Katie was talking about earlier, where you validate the effects of processing parameters, they would have understood that some of those fermented meats were not safe. They did not deliver the log reduction that you would need to make those products safe if the raw material was contaminated with 0157. So what we'd like to do is to make sure we give the message here about making sure you learn, you build in that important step in HACCP, which is reviewing your HACCP plan and looking at hazards that might be coming around the corner. Then we'll be following the general trend of looking at impact of megatrends on that supply chain, looking at the size of the impact, the risk balance, and then looking at solutions for the future. So then we'll be looking at unmet needs, residual risk, conclusions, and references. These case studies are intended to give practical examples of where the megatrends will have a real impact on the supply chain. Okay, at that point, I'd like to stop. The book is, we started talking about the book probably 2017 or thereabouts in terms of concept. We've developed those ideas in a really positive way. We're at a good stage now where at the next annual meeting, we will be building on what we've built so far for the design of the book. The intention is to talk a little bit more, and even in the past year, you know, things have changed in terms of our own world that have an impact, and we would probably make some changes to the way that we're looking at food safety, bearing in mind what's happened more recently. With that, I'd like to stop and then hand over to the MSCs.
Thank you very much, Dr. McClure, for your interesting presentation about megatrends in the context of the food security, food safety, and food quality. The next speaker is Dr. John Donaghy. He is Icmsf member since 2015. Head of Food Safety of Corporate Quality Nestle Switzerland. Dr. Donaghy will talk about big data, exploring possibilities for dynamic food safety risk management. Welcome, Dr. Donaghy.
Thank you very much for the introduction. Hopefully people can see my screen. We're already up and running, so that's good. And thank you, Pete, for the segue to this topic that I will talk about today. As you say, it's one of the mega trends that we will talk about in the new book 9. You know, it's one component. And I suppose the topic I'll talk about today is something that touches all of our lives, either our private or our professional lives, and that is big data and digital transformation. I think I'm still defined as someone who doesn't have a mobile phone, or someone doesn't use Google, or someone doesn't use booking.com or whatever, or social media. So we're all in this new era, let's say, of digital transformation and using big data. But I'm going to talk today a little bit more about how big data and digital transformation, can impact food safety management. And I'll divide my talk really across, I would sort of call it the 3 pillars, let's say. And firstly, I'll talk about the transformation as a new reality. How more and more we see authorities, we see industries, governments, etc., making use of data and making use of digital platforms for various aspects of food safety management. I will then talk a little bit about actually data itself. What does actually data mean in reality? And how useful can it be? How much do we need? What shape or form should it be in? And above all, I will caution about, let's say, what we want to get out of big data. One thing is having it, but it must have value. And thirdly, maybe of more interest to some of you, is that I will actually look at some concrete examples of where some tools, platforms, and big data technologies is actually being applied at various stages of the food value chain. I think probably, most of the audience, I presume, have an interest in food safety, and anyone with an interest in food safety, either in academia, either in industry, or in government or regulations, will be well aware of food safety recalls and the impact they can have on public health and the importance they have in terms of food safety management. And I think if you go back probably 10, 15 years and see how recalls were handled in some ways, and I certainly remember situations whereby, if a supplier or a retailer was making a recall, you saw an advert in a paper and you saw a notice beside the cashier's desk when you were actually paying for your goods at a supermarket. If you think now to how those messages are conveyed, through digital platforms, it's entirely different. Now you can actually, if a retailer wishes to do a recall product, they immediately have notifications on their, on social media, on their own websites. They also can inform the individual. In fact, last week I got informed by my supermarket of a particular recall for a particular product in the supermarket. And because I used a loyalty card in that particular supermarket, they had my contact details. So you see, immediately they can actually be able to inform consumers to remove that product from their cupboards, from their fridges, from their freezers, etc. So that is really a big advance in terms of using digital for managing the food safety recalls. And even from a regulator or an authority's perspective, the use of things like, bar scanning and these, let's say, chip and pins, and how people have paid and what they have ordered, for example, through various, e-commerce channels, through store cards as well. This also helps dramatically with with managing recalls or doing source attribution, when you have a sort of a, incidence of public health illness or a foodborne outbreak, then when you're trying to do traceback and trying to do source attribution, this is actually another avenue with digital platforms, how you can help with these tracebacks. So that's just one example of, let's say, how we've moved forward when you look back probably 10, 15 years ago to where we are today in terms of even managing recalls. And I mentioned there about the regulators and authorities as well. We see now many authorities and regulators as well as industry obviously embracing and having this notion of new tools, digital tools, use of big data, and none more so than, for example, the US FDA, where I presume many of you will have heard of the new era of smarter food safety. And this is very much embraced by the US FDA. And underpinning all of that, are the key drivers of technology-driven food safety, data-driven food safety, and traceability. And you cannot do those things without actually having good data, having good means of traceability, having integrated platforms, and having the data available at all parts of the value chain. So you see, this is becoming more and more important. And you see now on many publications, it is about digital tools, digital transformation, and the use of big data. But when we talk about big data, and if you look in any sort of publications, you always end up seeing what we call the different V's and of big data. And this is called like the volume, the veracity, the variety, the velocity, and the value. And if I asked you to say which of those do you think is the most important, I would hope you would say value, because volume is no good, if you don't make value or make use of that data that you have. If I give you an example of a Nestle, we do approximately 4 million microbiological analysis per year. Now, to make use of that data, if it's sitting in a LIMS system or sitting in an SAP platform, is it any use? Not really, unless you're actually interrogating that data to do some sort of tracking, trending, predicting, etc. So the volume doesn't really matter if you actually are not going to make value and used for decision-making purposes. Then when we come to variety, which is another element of big data, and it's very important in food safety management, as you will see from some of the examples I used. And what we mean is sort of a variety, and you could talk in terms of structured data or unstructured data. The 4 million data points that I talk about in terms of microbiological analysis, that is very structured data. That is, you have a microbiological specification, or you have environmental monitoring, and you have a result from Salmonella, Listeria, EB, other hygiene indicators. You have it available against a limit. So it's very easy to track, trend, visualize, whatever you want to do with it. But then if you have other information like unstructured data, so you have reports coming from risk assessors, you have reports coming from scientific journals, like Pete mentioned about the STEC 0157 publication. How can you incorporate that sort of data, because it's very much unstructured data, into either your early warning systems or into your management practice. So there is a wealth of information there, but it is what form it takes as well is extremely important. So that's, let's say, a little bit of my caution around the data. It's not about that big is beautiful. It is about how much value you can actually get from the data that you have and what format that data is in. Then where can we collect all of this data from a food safety management perspective? I think we all know that the food value chain can be quite complex, and some of the chains are actually more complex than others in terms from a global supply chain. But from a big data perspective, there's really 3 areas within the value chain where there's been a revolution in terms of the data capture, the data availability. And that is, one is in agriculture. So this is your upstream. Remember, most of the raw materials that we use in recipes, etc., will have either be plant or animal based in the main. So they come ultimately from farms, from land, etc. There is a wealth of information available here that actually can have an impact on food safety. Now, can we use that? And I'll come to that in a little bit. Certainly we can, if we can integrate it with other parts of the value chain. Then we have what I call the digital in production. So here we're talking about automation, Internet of Things, the Industry 4.0. You have equipment, you have machines that are now pumping out data by the second. How can you capture that data? How can you make use of that data? Either it's through CCP or critical limits, CCPs, OPRPs, cleaning chemicals used, concentration of cleaning chemicals used. All of this prerequisite programs, etc., are very much have a lot of automation built into them now, where you can actually capture data. To give you an example, in CIP, cleaning in progress, for example, you can have UV sensors that tells you the conductivity of your rinse water, for example. You can actually sort of optimize the use of, when we're going back to sustainability, you can optimize the use of rinse water and the amount of rinse water you need, and when you've actually used enough, or do you need to use more, but also in terms of even measuring other parameters in terms of how clean your lines are. So there's all sorts of sensors available in manufacturing now as well that we can use from a food safety perspective, and which can capture data. And then ultimately, you have your products going out to the consumers. And again, there's all sorts of data available there, almost like the feedback loop to what I would call the buy and make, which is the front two bits of the curves. So if, for example, you have for example, a bit like TripAdvisor for your hotels, if you have selling products on e-commerce, consumers can register either dissatisfaction or satisfaction with their progress. So you have automatically feedback. You can capture this sort of information, which you never were able to capture before. How many people want to phone and you congratulate you on your product about the sensory qualities? It's much easier to tick 2, 3, 4, or 5 stars on an e-commerce site. But this is valuable information. How much do you use this? It's the same on the other side. If, for example, you have an issue with a product, and it ends up being part of a foodborne illness or a foodborne outbreak, then there is a lot of digital information available there in terms of epidemiology, consumer uses, consumer trends, the reports of illnesses linking to sort of hospital public health data, etc. So at the very end game, there is a lot of digital information and big data available as well. So hopefully you can see from this simple graphic that there is loads and loads of opportunities to actually gather data along the whole value chain. And this has sort of led to this sort of concept a little bit where we call this interconnectivity between what I call precision food safety, precision agriculture, and precision production, because these three elements are very much interconnected and intertwined, and all the data that is gathered at each of those steps, you have to be somehow managed and, as I say, be able to extract information that is useful for dynamic risk management from a food safety perspective. And I'll later go through some of these individually and talk about some of the elements. But I want to just give you here as an example, and we produced a position paper as part of the Book 9 production. And this position paper is really talking about dynamic risk management and how we can use data. This sort of graphic is from that publication, and it shows you, for example, in a leafy green value chain. You start from the top left-hand side, you have the field. So you have your agriculture, your precision agriculture. You have then your let's say your harvesting and packing, then you have your cutting, and then you have your distribution, then it gets to retail, it might go to manufacturing. But then, as you saw, for example, from some of the recent outbreaks in the US, then you have perhaps illnesses as a result of this value chain. So is there data that could be collected along this chain that could prevent those sort of outbreaks, or could allow you to make dynamic risk management decisions along the chain based on the data that you can see upstream? But you can see in this graphic the different stages that where the data you can collect. You can collect data on animal intrusion, you can detect data on actually the people, personal hygiene, cleanliness, vaccination of workers. You can look at water quality, again, very structured data. You can look at, very, very many different types of data. But I always caution against the fact that sometimes the data can be very complex. It is difficult to integrate it between the different actors or players along the value chain. So And this is why I say we have to really ensure that you have good interoperability among the stakeholders, because remember, you have farmers at one side and you have a consumer at the other end. In between, you have many, many different actors, and you might have even global value chains or global supply chains. You could have a product at the end that's a mix of many different commodities that have been used and maybe manufactured at different parts of the world from a global perspective. So being able to capture all of that data and actually have it in a system whereby you can actually make a value decision in terms of risk management. I would say we are getting there, but there is still some way to go. And in this publication that we produced as part of the Icmsf, you will see here we also tried to create what we call the dynamic risk management system. So this is a bit like a dashboard. So we sort of hypothesized, well, what different scenarios could we have, for example, along the leafy greens value chain? And could we intervene at various stages to actually influence the next step down? And it's a bit like looking at the conceptual equation of Icmsf. So if you have your H0, you have the value at the beginning, let's say in terms of level of contamination. You have your reduction step, you have your cross-contamination step. Is there something that we could capture data for example, at the H0 end, and then we could make a decision at a later stage, say, look, I have to apply a different reduction step based on what I see at H0. Or if I see that if there's failures in my reduction step, or if, for example, there's a substantial increase in my recontamination step, what can I actually do in a dynamic way to manage that risk? It's a little bit of a conceptual approach at this stage, but I think with data and being able to, let's say, integrate the data from the various actors and the different steps of the value chain, this is a sort of where I think we can go in the future with regards to the use of this of data to have a dynamic risk management system. Then I would like to take you through each of, let's say, the chains of this sort of a tripartite, I call it. And I'd start with precision agriculture. What sort of data can we actually get at a farm level that would be useful in terms of food safety management, downstream? Now, and I think if you look at any of the large farms, there is a lot of technology there. And if you just Google smart agriculture, precision agriculture, you'll see the use of drones. You'll see the use of built-in computer systems, even to large tractors, combine harvesters. These sort of digital systems are able to capture weather data. They're able to capture soil humidity data. They're able to do with drones. You can look at geospatial layout. Is there flooding in the area? Is there bird, let's say, infestation in certain parts of a crop? And then that can direct you not to actually harvest that area of a field, for example, or not to, let's say, you harvest parts of the plants that are there because of the data that you can capture. And this is, in some cases, it's mycotoxins because it's about cereals. And, if you have bad weather conditions, you can lead to sort of, mold infestation. And ultimately, you could have a high level of mycotoxin. So it's better to avoid parts of a field or parts of a sort of a crop, or is better to sort of harvest early or whatever. These are sort of data that is available that can direct you towards, let's say, operational aspects, but also helps you with your risk management at a later stage. Also, you can capture things like global gap, certification and audit certificates. If you see that from your certificates from farms, for example, that you see a lot of gaps that have not been filled and require action, then this could influence you in terms of, the purchase of that material, the use of that material further downstream. So again, lots of different data available here. The question is sort of which data do you take and can you use it further downstream? And blockchain is one of these tools that I think it's worth mentioning here. Sort of a blockchain is sort of like a platform that tries to link all of the aspects of a commodity from upstream right through to manufacture. And again, I caution a little bit, and there's been very, very many experiments done with different blockchain technologies, more for a traceability and a transparency, and even for authenticity purposes. But I've seen it less used as a reactive tool for food safety, but it has that potential. because it has a means of tracking, capturing data, logging the data as a ledger from one actor to the next actor. So all of this data accumulates as you go along the value chain in this ledger of that particular product. But of course, that will work nicely if you have a very integrated supply chain. So I'm taking animal carcasses from one farm to one abattoir to one, let's say, to a retail food chain. That may work. But if, for example, in the leafy green story, you start with a lettuce or leafy green in a field, can you track that the whole way through in terms of then it's sold as a whole lettuce, it's sold as a part of a sandwich, it's sold as cut lettuce. This is where the traceability from a food safety perspective does get a little bit more complicated in terms of the use of blockchain. But it is a tool. I think it would be remiss of me not to mention it as part of big data and digital transformation in the food chain, because it is, it has been embraced by many of the actors to try to link this data. The other third part of the of this sort of like a three-legged stool is a precision food safety, and this is a sort of a term has sort of been coined by COVID et al. In 2017. And when they talk about precision food safety, what do they mean? Here they talk about, let's say, the explosion of genetic data that has now become readily available. In the past, you might have had some phenotypic data around some of the organisms that you isolate, be it for food safety, be it quality, be it spoilage or whatever. But now we see with whole genome sequencing and next generation sequencing, we see a lot more detail in terms of those organisms and in terms not only their phenotype, but their serotype, but also their genotype and also virulent genes that they may have present. And these sort of all of this information also helps with actually risk management decisions. And we see this even from some of the regulators, some of the authorities. When we see surveillance data now being produced, we see graphics like this. This is from, for example, the European Clinical Disease Centre, the ECDC. Here you can see sort of through their surveillance data, and they're not just doing surveillance just for particular organisms, they're even doing surveillance with particular let's say, antimicrobial resistance factors that are in some of these organisms. So this allows you to even look from a regional perspective where you see the movement of certain strains, across different countries within a region. So again, this is all valuable data as part of a risk assessor's toolbox, but also as a risk manager's toolbox. And one of the other areas in terms of precision food safety, which has really probably came to the fore in the last decade, has been a whole genome sequencing. And this is for building the databases such as Genome Tracker. And this more or less is trying to build a database of pathogens worldwide, let's say. It's primarily sort of administered through the US, but there's many other laboratories around the world that contribute and input strains and their raw sequence data into this genome tracker. So you can see this is a really valuable tool when it comes to foodborne outbreaks, traceability, source attribution, etc. And you can see how this has actually increased in terms of the amount of data that's in it over the last decade. We're now talking almost 1 million strains of pathogen strains, and these have been strains that have either come as clinical isolates or have come from different surveillance studies that have been conducted. So again, this is precision data, genomic data that is now available, which probably was not available 10 years ago. So again, if we look back at my three elements before, at the consumer end, if you have foodborne illness, you can see where this can be extremely valuable in terms of source attribution. Then when it comes to precision production, and again, some of these examples I'm giving are just one-off. This is not an exhaustive list. There is many, many examples. But if I take from the food producers perspective, as I mentioned before, we in Nestle globally, we do about 4 million microbiological analysis per year, either raw material monitoring, raw material release, environmental monitoring, finished product testing, other verification, microbiological analysis. But to be able to make use of that data, you have to first visualize and see what you're doing. So we use tools like Power BI, et cetera, that actually can accumulate this data. And so we can see I can see from a global perspective now what factories or how much analysis are doing across factories. I can benchmark, I can track, I can trend, I can even trend my data on a weekly basis in terms of EEB or hygiene indicators, deviations. This allows you to see things like seasonality. It allows you to see some detail within certain factories, within certain regions, and maybe link that back to raw material supplies as well. Do we see these trends? So again, having this visibility on some of this data is immensely important, from a manufacturer's perspective in terms of your tracking, tracing, and I think as Bob mentioned earlier about your early warning systems as well. So that you don't have a large deviation and you've not had any early warning. But of course, then we take it a step further down to an individual factory level. And again, we use tools. And again, this is, we see many manufacturers offering, or many sort of commercial companies offering similar tools. So this is linking your analytical results with your environmental monitoring sampling plans within your factory. So literally you can have a 2D, or on the right-hand side of the screen, a 3D diagram of your plant. You know where all your sampling points are. You take your data from SAP or wherever database you have, and you link directly to those sampling points. So instead of looking at an Excel file and looking at 6 months of data and see when I may have had a deviation, this is actually in real time. So as soon as your analytical results is available, it's populated into your sample point, and you immediately can track and trend, where I'm actually having a deviation. Do I see my bubble getting red? Do I see my bubble getting larger, based on the number of samples I've had to take around that sample point? Do I see it getting smaller, etc.? Or am I missing vital points? If I do something like a swabathon, to going back to the WGS, for example, if I do an intense swabathon, can I spot areas from my factory as an overview where I actually have maybe persistence or harborage of strains? So all of this, and it may only look like visualization, but all of this, data gathering and being able to visualize that data really does help with your tracking, trending, early warning, prediction, etc. And then I always like to show this graphic, which is I think I stole this from someone else, and they say it's from the New England Journal of Panic-Inducing Gobbledygook. Okay, so if I look at what does it say, and this is all about early warning, I look at my arrow and says coffee can cause depression in twins, but this is from a food safety perspective. You always have to be aware, what are the monsters coming over the hill, and are they new, or do I have to manage them in some way? So it may be, for example, a new pathogen because of climate change, going back to for example, the book 9 sort of some of the trends, emerging issues. If it's new pathogens, because of climate change, or is it a new vehicle, of a traditional pathogen that is actually starting to emerge? So we have to be very much aware and be able to manage and to able to decide if it actually is something new or not. And we manage this through, you have a detection method of early warning, you have to try to understand the risk, you evaluate the risk, and then you decide, do I need to do something about it? So early warning is an extremely important part of either a government or an industry in terms of food safety management. And what we see now is many different commercial tools available, and everybody can sort of, pay your money, take your choice, or build your own if you wish, in terms of early warning systems. So we see lots of tools now available for what we call predictive analytics. And again, this is taking the data that is available in the public domain, maybe data that is available through academic surveillance, looking at recalls, looking at outbreaks, etc., and trying to predict trends, of emerging issues. So you almost get a sort of an early warning of what is the monster that is coming over the hill. So again, early warning is an important part of food safety management. And now we see more and more tools, again, graphically illustrated, like these sort of dashboards, that can actually help us with that data. But of course, it still requires expertise to be able to look at the data and be able to analyze and really assess the risk associated with it, say what the data is, the predictive data is telling us. And so just to finally to summarize, I again use this cartoon, and what I go back to my value statement. As the person at the head of the table is saying, let's solve this problem by using the big data. None of us have the slightest idea what to do with. And I think this is before you start gathering and having nice tools for data gathering. You must know, what am I going to do with my data when I have it all pulled together and what it is showing me. I now need to have a use for my data. And it's important in terms of risk prediction that your data is accessible. So of course you need volumes of data, you need it accessible, and you need it to be clean. Often we see now a lot of the data is not clean. The metadata is not good. So a data analytical point is not much use if you don't have good metadata associated. So it must be acceptable. And my big final say is that it must have value and it must be actionable. So that concludes it from my side, Francisco, and thanks very much for listening.
Thank you very much for your presentation, John. Very illustrative about the use of data and big data in food safety. Now we have time for some questions from the audience. We already have 4 or 5 questions on the board, so I will go to there and read them so any of you can answer. So the first one is, considering that sampling has to be random or must be random, are there Icmsf guidelines for random sampling, particularly for large batches?
And maybe since I'm still on the off mute, I'll have a stab at that, Francisco. Yeah, for large batches, the key is random sampling for sure. And we get lots of questions like this. And I always say you try to take samples that at least are from the beginning, middle, and end. And I think to Bob's point earlier, depends if you have a situation whereby it's an intervention by an employee, you get a one-off contamination. Or, for example, you have the drip from the condensation, you maybe see. So the spot of contamination, can be very irregular. So we always try to have a sort of at least a start, middle, and end of the batch. And often we get asked the question, particularly in suppliers, and I always say to our suppliers, if you have an auto sampler, that is even better, because they're your drip feeding samples, from an auto sampler. So you imagine every 30 minutes of a sort of a one-day run, every 30 minutes you're taking 1 gram. That let's say composite auto sample is actually as good a representation of your full batch as you possibly can get. It's probably better than at the end taking 225 grams at the beginning, 2 at the middle, and 1 at the end. If it's 5 samples you have to take. So it's I think randomness is extremely important. I always say that to be able to to catch the heterogeneity of contamination.
Thank you, John. Any of the other speakers want to add something? If not,
yeah,
go ahead,
let
Bob.
me jump in here. One of the points I was making in my presentation is that if you're dealing with normal distributions, what you want is random samples. If you can no longer assume that you have a random distribution within your population, there are alternative approaches in terms of sampling and sampling sizes. That's when you may want to move to a stratified random or a systematic type of a random. Really what you should get is some idea of how the contamination is likely to be distributed. And then you can always do things like chi-square tests, et cetera, to evaluate that. But ideally, you would do randoms when you can't make any other assumption. The other thing is when you're mixing a sample, okay, when you go from a large batch and you mix it all together, you're basically normalizing the data. So you would move from a less than random distribution to something that is more random as long as you start blending them together. So again, the best thing to do is to talk to somebody that knows the statistics of sampling to get some help.
Thank you very much, Bob. So here's another question that I think probably Peter or John may start answering. Nowadays, there are several novel foods that are different from traditional foods: plant-based, insect-based, food from fermentation processes, and so on. What are the microbiological criteria to apply to these kind of products? Which parameters should we follow?
That's a good question. I think probably the first, if there are no established micro criteria for those products, I would probably suggest to see if you can find an equivalent product that is made using the same raw materials, the same processing steps or similar processing steps. So, for example, the fermentation process one there there would be micro criteria set for other fermented products that could be applied. There are a couple of good documents that have been put together. One is, I think there's a Camden document, Camden BRI guideline on how to set micro criteria that sets out the steps involved in setting criteria, and also the Icmsf books as well. So they lay out the principles for setting micro criteria. What we were actually looking at within book 9 was, in the fit for purpose criteria section, was to produce a stepwise diagram of like a process flow diagram of how to set criteria. We've got a straw man that we've developed for that, but not finalized yet. I think that will help this question as well. So that the work going on with that fit for purpose criteria, that's another chapter of the book that we were hoping to put together a position paper to publish. So maybe we can take this back into Icmsf for our annual meeting to see if we can develop this further with Sushard, who's leading that activity. John, anything to add?
Yeah, no, I think you're right, Pete. I think you follow that sort of like straw man sort of decision tree with respect to how you set the criteria. I think one of the things that's important is that we probably, something like plant-based, I think we have to start to understand the microbial ecology of these sort of products, because I think what we have seen, you just don't cut and paste from a meat-based product, if it's like a chilled or frozen product, across to a plant-based analog. In terms of, if we go back to the listeria story, what supports growth and what doesn't support growth, and what predictive models are available, do not necessarily exactly apply, for a meat-based chilled product compared to a plant-based chilled product. So, and this is why I think there is still, I say it's in its infancy in terms of understanding the microbial ecology of these sort of products. We see it even, for example, in beverages, where you're replacing, let's say, animal milk with oat milk or rice milk. And sometimes if you have time temperature storage conditions, again, we can see very, very much differences, because as you can imagine, an animal milk may have different levels of bacillus, for example, compared to a rice milk. And in terms of, when you're looking at some of your processing conditions, like time temperature storage, for example, in a buffer tank, then you have to really take this into consideration. And this is still, I would say, there's still a lot of unknowns around this.
Can I jump in here for a second?
Yeah, go ahead, Bob.
Yeah, I would, and maybe Wayne can also support this. When you're trying to determine what kind of microbiological criteria you're going to use, the first thing you do is check with the whatever jurisdiction you're working with. You read the regulatory guidance that is provided by the government agencies before you do anything, because you may want to come up with a regulatory criteria. You may come up with a criteria that doesn't match at all what the agencies are going to actually be requiring or interpreting. And that takes somebody that is familiar with reading all of those regs and documents, et cetera. And I don't know, Wayne, what would you recommend?
Yeah, similar idea, Bob. I mean, at the end of the day, if you look at criteria, a lot of the time they're set for sort of categories of food as opposed to specific foods. So you might get, like in the EU criteria for listeria in foods that support the growth of listeria. I mean, what are they? They could be some of these new foods that come about. So it is very much about doing that sort of hazard analysis, generating the data. John's talked about this. You can't just pull out micro criteria out of the woodwork. You've got to have some basis for it. That's where research comes in. But yeah, Bob's right. Check the legislative point of view for a start off. It's always a good place to start. And if the product isn't covered at all, then obviously you've got to generate your own specifications based on data. But if the product is covered, then you start off with those criteria and then work upwards from there if you need other ones.
So it's an area that is likely to be up in session 6 when we talk about listeria. I know here from the United States, you have 2 different agencies. Their policies for listeria and their corresponding criteria are based on different regulations. And you have to know which agency is actually responsible for the product you're dealing with.
Yeah, and I think, Bob, that's the challenge. I agree. You should understand the regulations in the country you're operating in. But if you're in a global environment, and I think as Wayne has said, sometimes you have horizontal regulations and sometimes you have product-specific category regulation. And as you say, you then may, within a country, have something different on ready-to-eat and non-ready-to-eat, which some of these plant-based proteins may belong to. So that's the sort of, let's say, the complexity. Maybe from I'm saying from an international perspective, if you're operating just in one country, it's easy to understand perhaps what is in that country, but when you're trying to operate globally, it ends up that you're trying to do a mix of everything, to come up with sensible criteria.
Yeah, well, if nothing else, what you want to do is look up and find out if there's a criteria that's been established by Codex Alimentarius, because at least all of the countries I know of are members of Codex, and they may not follow those guidelines all the time, but it's a good place to start.
Yeah, that's a good point, Bob.
Thank you all. I will try to put together 2 questions now. They are not exactly related, but I think we can elaborate because they are continuation of what you have been discussing so far. So the first one is, how can we correlate risk assessment with defining the appropriate level of protection and food safety objectives and performance objectives for industry? I think this one is going further in what Wayne mentioned in his presentation. And the other one that is already up is, what is the future of food microbiology for cellular foods? What are the advances in the microbiology control for these kind of cell meat foods, or I will call them lab foods more than just cell foods? So any of you?
Okay, I guess I better start on the risk assessment, risk analysis side. I mean, at the end of the day, what I've been talking about, food safety objectives, POs, all of those things, those are risk management metrics. Those are set by risk managers to define a appropriate level of protection. So for once, maybe you could look at it as a quantitative risk management to some extent. And that's important. But obviously, we look at the whole control of food safety in terms of a concept of risk analysis, which has the risk assessment element and the risk communication. But leaving the risk communication aside, on the risk assessment side, you've got a similar trend. You've got the quantitative risk assessments that can be done. And if they were done in, say, a pathway approach, then you could be using those quantitative risk assessments to sort of look at mitigations, for instance, so you might achieve some of the risk management metrics that you want to achieve. So they are complementary. And a lot of the time, setting a risk management metric is probably pointless if it can't be achieved in any way, and that's where risk assessment comes in, to be able to look at see whether it can be achieved, whether there's mitigations in there that you can do to achieve that PO that you've set. And it's a blend of the two coming together. And I don't know if Bob has anything else to say on that, because you probably thought deeply about this.
Yeah, I've thought a lot about this, and that's an interesting group of products that's on the horizon. And what I'd say is, to start off with, we don't have any real, similar product that's marketing. but you do have a lot of products that are produced by processes like fermentation. And the integrity you have to maintain of a fermentation, not allowing contaminants, etc. I was going to say, if you would want to start looking to where that might be going, go back and look at what's done for the fermentation industry. And that would maybe give you some hints on where the regulatory agencies might be going in the future.
Thank you. Anyone has any other point to make? Peter,
yeah, Francisco. Yeah, yeah. On that point that Bob makes about the fermentation, I think that also applies to the lab foods that in this question later on. That I think when you think about cell lines that might be used, then the checks that are in place now for fermentation processes like starter cultures and those sorts of things, the genetic confirmation that your starting cell line hasn't changed and is maintained, those sorts of things would need to be considered for these types of foods. And although intuitively you might think that a lab produced protein might have all the controls in place already needed for it, I think there's some out of the box thinking that needs to go on for these products that, you know, some of the controls we probably don't have in place at the moment and will need to be put in place to ensure that there are no risks. And that goes also to non-microbiological risks as well. So toxicological or other, maybe even allergen risks, those sorts of things would need to be considered as well.
Absolutely.
Thank you very much for all. So I think we have one more question already. So here is. So my country has a regulation for Bacillus cereus in powder milk. The sampling plan is N equal 3, little m equal 100, big M equal 1,000. The sampling results were 102, 98, and 105. Should that batch be rejected?
It depends on whether you're working with a 2-class attribute plan or a 3-class attribute plan. And again, that's one where what you're talking about here is a regulatory limit. That's where you look for guidance on what has been provided by the regulatory agency on how to interpret the data.
Yes, sorry, I missed one small piece of information. The C is equal to 1.
So it's a 3-class plan.
3-class
it's
plan.
A 3-class plan.
And two of the results are outside. So you've got C. If you had C equals 2, you'd be okay, but C equals 1, you're not okay.
Yeah. So in the example given, then this would be a failure. Whether what you would do with the product afterwards then is part of the micro criteria, as Bob went through in his presentation.
Yep. Thank you very much, all.
Maybe in these sort of circumstances, Francisco, because quite often you end up in these sort of situations, from in a manufacturer's perspective, when you're on that line, but I think this is where I always say it's important about the tracking and the trending. Is this a one-off, or do I see my shift in my curve going to the right-hand side more towards my M? Do I see if I look at my distribution curve, do I see a regular, is it a one-off that I see, I have 3 samples or 2 samples above the 100, but if I'm seeing every time I take my 3 samples, one time it's 105, then it gradually moves towards 500, 600, and I see a deterioration of my system. So I think you have to look as well in the bigger context as well. If it looks like a systematic failure or deviation in your conditions.
Well, yeah, and to add to that, if this is potentially related to raw materials that you're sourcing as well, so it's good to apply that concept and that principle that John just mentioned to your raw material suppliers. Look at the quality of those materials to see if there's anything out of kilter, out of sync. And it's important to have the batch to batch variability data that Bob was talking about earlier to be able to determine that.
Yeah, and let me emphasize here, this is why most of the agencies, at least in the United States, focus on the primary system for looking at control of listeria is to do listeria species as an indicator organism and to take action before you ever get close to the limit that's going to throw you, into in harm's way in terms of the regulatory agencies. That you need to be looking at your trend analysis and, if at all possible, using an appropriate indicator organism.
I, as a regulator, agree with all of that, but I will say one thing is that in this question, it says it's a regulation for Bacillus cereus. And as a regulation for Bacillus cereus, it'll either say, if you fail, you should either withdraw or recall, or you should improve your hygiene. Depends on whether it's a food safety criterion or a hygiene control criterion. And whatever it says is what you do, because that's a regulation. But I agree, just doing that and ignoring it isn't the point, and that's where what John said comes in. You've got to have been looking at this, and with a bit of luck, actually, you should have spotted the trend before it's actually gone over the threshold, at which point you have to then comply, because if you get inspected and you've done nothing with this, then you'll be cited.
Thank you very much for everyone, and thank you very much for the audience for the questions. We don't have any other question on the floor so far, so I give the floor to Jeanette to close the session.
Thank you, Francisco. On behalf of the Latin American Subcommission of Icmsf, I thank the speakers for their presentation and participation in the discussion session, and for the great contribution to success of today's webinars. We hope the participants have enjoyed it. Before ending the session date of the webinar, we would like to acknowledge our sponsor, Merck, Institute of Food Technology, and Food Research Center, without whom it would not be possible to offer this free webinar to so many people, not only from Latin American countries, but all over the world. Also, we would like to announce the Latin American Congress of Foods. I don't know if I can share the screen.
And you can go ahead, Janet.
Yeah, okay. 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 The Latin American Congress of Foods look into food systems to be held in Medellin, Colombia on November 15 to 18. The deadline for abstract reception is in June 15. You can see the link to the Congress website. And we hope you can participate. Do not forget that we'll have 2 days more. We wait, and thank you, and goodbye.
Thank you, everyone. Have a good afternoon. See you tomorrow.
Thank you. See you tomorrow. Bye-bye.
Bye-bye.
See you tomorrow. Goodbye.
Bye.